Good morning, everyone. So, on behalf of Emirates Aviation University, it gives me great pleasure to extend a very warm welcome to all of you here for the first International Conference on Data Science Application and Advances. This is a landmark event bringing together researchers and professionals to explore how AI and data science can drive sustainable solutions for a climate-resilient future. We are honored to host delegates from across the globe who bring a wealth of expertise and diverse perspectives to this conference. The theme of ICADA 2025 is building a climate-resilient and sustainable future. Today, this conference will provide a platform to share the latest advancements in AI and data science and to discuss how new technologies can be applied across the sectors and to address urgent challenges such as climate change, sustainability, and environmental resilience. The topics we will cover range from AI for climate and environmental modeling, predictive analysis for disaster resilience, smart cities and climate adaptation, to sustainable aviation, green airport management, and ethical AI for responsible innovation. This diversity underscores the interdisciplinary nature of this conference and the need for us to collaborate on approaches for the global climate changes and challenges that we have. I would like to sincerely thank you all for being here, and to our keynote speakers, sponsors, strategic partners, and the organizing and scientific committees who have worked hard to make sure that this day is here today and have this dedication to this event. Your support is greatly appreciated. I hope that ICADA 2025 inspires new ideas, fosters collaborations, and provides actionable insights that contribute to a sustainable and climate-resilient future. I wish you all a productive and engaging day at Emirates Aviation University. Thank you so much.
Thank you. We will now start our first session. Our first session is titled From Algorithms to Impact, AI, Remote Sensing, and Climate-Resilient Innovation. Our first keynote speaker is Dr. Dirk Dongnickel, Senior Vice President of Enterprise Data and Analyticals at Emirates Group. Please join me in welcoming Dr. Dirk to the stage.
All right. That's okay. Good morning. I hope everybody is awake after the first coffee. And thanks for the opportunity to speak to this audience. It's a pleasure to be here. I come a little bit more from the practical side, despite my vita, my speaker profile, which popped up briefly. I have a very theoretical academic background myself. I worked in academia for a long time, but in physics. But nevertheless, I mean, for the last 20, 25 years, I've been more involved in practical things, in particular practical application of data science and AI, everything around data, and in different capacities. I mean, working for consulting firms in the telecom sector, and now the last 7.5 years for the Emirates Group. So I would like to talk a little bit about what it actually means to apply data science and AI in a corporate environment like Emirates. And to start with this, probably don't have to mention too much about the AI hype, which has been with us probably for the last couple of years. Ever since ChatGPT hit the floor, I mean, people refer to this as the iPhone moment of AI. Of course, AI has been around for a much longer time in the form of machine learning, optimization algorithms, and has been applied. But of course, that triggered an enormous hype. And the hype is reflected in, of course, in tons of headlines, white papers that you can read. I mean, it's hardly difficult. I mean, it's almost impossible, I would say, to open a newspaper these days without reading about AI. Numbers encoded here, what I chose is a forecast from McKinsey about the anticipated spend on just the related infrastructure for AI, and this is mostly generative AI, of course, large language models, until the year 2030. So over the next 5 years includes 2025. When you look at the numbers, I mean, it's staggering. I mean, we're talking about $1 trillion almost macroeconomic bet that's going on at the moment. So there is a tremendous hype about this. I mean, it's also the acceleration that is visible in the spending. It's almost scary for some of us. I mean, I've been around a little bit longer. It's a little bit reminiscent maybe of the dot-com bubble around the turn of the millennium. Maybe we will see some similar outcomes. Nevertheless, I mean, there is substantial spending, and which is a reflection of substantial expectations of value to be generated from these capabilities which are out there. Now, there's another side which is also interesting to look at. I mean, it's a recent it's an MIT study which was published recently, estimating failure rate of AI initiatives around 95% in corporate environments. So you assume that 95% of the investment is a failure. That is a pretty dire picture, I would say. It's probably also not quite as bad, but this is of course substantial, and it's not entirely new. I mean, I put some a little bit older quotes down there. The last one in the end was from a Gartner discussion, I think from 2019, before the generative AI hype, more referring to kind of conventional predictive, prescriptive analytics capabilities in the form of conventional machine learning. Also there, close to 90% failure rate. Where failure, we have to be careful to describe that also, what that means. Nevertheless, I mean, this is a huge disparity between investment and expectations on one side and then corporate reality, at least on the other side. And it might be worthwhile looking into this. What is actually going on there? Why is that happening? Why is it so difficult? And it is difficult to get these things into a corporate environment and make them work. Because, I mean, everybody has played with ChatGPT, I suppose, and some of the competitors like Gemini capabilities look marvelous. And the opportunities are also not difficult to come up with. I mean, how this could be used and how this could be applied. The question is, why is it so bloody difficult to get these things into business operation? And that's what I want to talk about a little bit. I mean, it's a story in, if you like, in seven chapters, 7 reasons. And to explain, from my perspective, at least from my experience in this field, what usually goes wrong. So it's a little bit negative connotation of my presentation, but there's a lot to be learned from that in what needs to change in many organizations actually doing this. So let's look at a simple example, and I'm not using a fancy generative AI example. I use something which we have done in Emirates for the airline already quite some years ago. We are predicting the consumption of hot meals in business class. And it's relatively straightforward. I mean, you have typically in business class, I think, 3 hot meals which are being offered. On one hand, you want to make sure that your customers and your passengers get what they have ordered. On the other hand, you also don't want to unreasonably over-cater and carry 3 hot meals for every passenger. So it's this relatively straightforward machine learning example. It's not rocket science at all. I mean, it's something that you can actually build on a laptop, provided you have the necessary data. And, but it's a nice example to demonstrate what can go wrong in these kind of relatively simple cases. And it's very, very similar now for generative AI applications, I mean, which we have also built in Emirates. And you run into very similar challenges as the ones which I'm describing now. So as I said, it's a straightforward project. What could possibly go wrong? Now let's start with one of the most difficult things is an accurate, very precise framing. What is it actually you're trying to do with data science, with an AI solution? The first thing that jumps to mind, of course, is minimizing food wastage. Because if you want to make sure that everybody gets the hot meal they desire on board, you have to bring 3 per person. Leads to 2/3 wastage and associated cost. But at the same time, you also need to ensure that every customer actually gets what they want. Because, I mean, we have a premium product in the airline, and it's very awkward to tell somebody who has paid thousands of dollars for a flight ticket, they want red meat or chicken, and you have to tell them, oh, sorry, we're out, but we have an alternative. That should not happen very frequently. So, of course, when people start thinking about this, typically they go for the waste. They try to really kind of build something that predicts accurately and then minimize wastage. But in reality, it's an optimization problem. You have probabilistic input, but you need to optimize at the same time for customer experience. Customer experience in the form of customer first choice met. So the framing of the problem is actually quite important because it also means you have 2 different stakeholders. On the left side, you will certainly have the CFO or somebody who has to manage the budget of a catering department and has constraints how much money they can spend. On the right-hand side, in many organizations nowadays, you have somebody who represents customer experience. And if you forget to frame this correctly from the beginning, you forget one major stakeholder, and that stakeholder will make sure that you don't launch what you have built in many cases. You will never get this into business operation. Yeah, so it's a critical one. Actually, there's another challenge in this, of course. When you look at it, the two things you're trying to optimize for, they're competing, and they're very difficult to compare. On the left-hand side, you have cost. On the right-hand side, a customer experience metric, or KPI, which says customer first choice met. Now, how much value do you attribute to your customers, maybe 1% of your passengers on each flight getting their first choice more than if you wouldn't have that model? So in reality, it's a very, very difficult thing to crack with different stakeholders. And the next question, of course, that then comes up after that's clarified, and if you don't clarify these things up front, you have a very high likelihood to this thing never seeing the light of day, despite the fact that you might have a very good data science solution. The next question that comes up typically is, do you actually have the data for doing this? It's not difficult to estimate that what you need in order to predict hot meal consumption on a flight. It's very much the historical data of what have passengers of certain demographics on certain routes, night flight versus day flight. I mean, it's not difficult to estimate or to assume what the right features are for such a machine learning model. The problem is, do you have the data in order to do this? Sounds relatively straightforward, but you need a couple of more than 20,000 flight attendants, so it's actually in business class it's a little bit less, but a couple of thousand flight attendants systematically capturing this historical data. Otherwise you can't build the machine learning model. And the first thing you will find in this example, for instance, or which we found a couple of years ago, is we had all this data. The reason why we used this, or why we built this for J-class, for business class, was that our flight attendants actually have a tablet and they take the order of the passenger. The problem, however, is that they don't necessarily capture the first order. They capture what they deliver to the passenger, because it's much easier. Instead of 2 data entries, it's just 1 data entry. And this is a general observation, I think, in these kind of situations, that data is very often an afterthought. The quality of data and the data that's being captured is an afterthought in business process design. In that case, the transaction was designed to deliver food, not necessarily capture everything that's relevant in that transaction, because analytics is an afterthought, machine learning, anything around analytics. And the other thing, of course, you want to compare cost with another metric, which is customer satisfaction. You need something else, which is, luckily we have something which actually relates to this. It's the overall satisfaction on flights. We have very, very high response rates on this in the range of 35 to 40%, or so in the millions, literally. And you can study what's the impact of people not getting their first choice meal in a statistically significant way. So that's possible, but the most important message here is that the data that you need might sound very, very straightforward. And then, let's say in a research environment, usually you work with data sets. I mean, they're clean, they're prepared, and so on. If you have to collect this, we had to actually go back and retrain, or not my department itself, but we had to work with our service delivery department to make sure that flight attendants actually understand the importance of the data being captured accurately before you can make this work. As I said, the algorithmic part here is very simple. Getting the right data is the challenge. Yeah, so in some cases, and this is a good example, I mean, we actually had to change the business process. It's a minor change, but it's quite substantial with a couple of thousand flight attendants to make sure that we actually have data of sufficient quality. The next one, and I love this, I just put a slide, it's an old quote from Andrew Ng. Probably you don't have to introduce the gentleman for an audience like this, but you need to manage your data foundation. You need to build a data foundation for analytics purposes. Many companies have lots of data distributed over lots of different systems. I mean, we're dealing with hundreds of different systems on the airline side alone, on the Emirates side, with inconsistencies, overlaps, and everything you can ask for. You need to build a proper data foundation, which in a company like Emirates can take years and substantial investment before you have anything on top of which you can actually build and scale AI solutions. If this is not done, you won't go very far. Data foundation is an absolutely key ingredient. It's not good enough to have that data sitting somewhere in the system and always take it out. You usually don't have the quality and it's not modeled in the right way. You can also say, I mean, for me, is data science and AI is a little bit like, I don't know, Italian design furniture in your living room. If you don't have a basement, there's no house on which you can actually build a living room and install the design furniture. Plays a critical role. Very often overlooked, in particular these days with the hype around AI, that everybody tries to do something with AI, and you can do something with AI. If you want to scale it, you need a solid data foundation. You need a solid foundation for your house, otherwise this is not going very far. All right, and the next one is also, it's a favorite of mine, is nowadays I don't think it's that much of a problem anymore as it used to be maybe 10 years ago, but still you find that very often in many large companies. There's a profound difference between building a proof of concept, a pilot or something like this. I compare that with a laboratory setup on the left-hand side. Building something in the lab is one thing. Scaling it for industrial production, so on the right-hand side, is a far different environment. It's a far different challenge. And this is actually where, from my experience, still lots of data science and AI initiatives get stuck. Call it the graveyard of data science and AI initiatives. It's the POC environment, the pilot environment. That something works on a laptop or even on a large server, but it doesn't scale up to operations, to real operations. So you need a path to production. And we call it path to production in Emirates. I mean, it's one of the things we started quite some time ago, 6-7 years ago, to build the necessary capabilities. There are many different reasons for that, but what very often happens is you have data scientists delivering a working data science model, meeting all the different necessary requirements in terms of accuracy. All of that is fine, but you need to be able to deploy this into a production-like IT environment. And unless that path exists nowadays with modern CI/CD capabilities, the challenge is typically that your IT colleagues will basically say, well, I didn't build this, I will certainly not run this for you. Yeah, so they will, in worst case, even start recoding what has been developed by a data scientist in Python and say, performance isn't good enough, let's do this in C. These things still happen quite frequently, and there are all kinds of different challenges. And it's not just that the algorithm has to run in a stable production environment. Typically, you have dozens of different data pipelines. Right? That's what you can see on the right-hand side with the example of a pharmaceutical or chemical factory. It's very much the same picture. These things are developed very often with data extracts, with data dumps. But you need stable production-like data pipelines, and many of them in order to calculate your features on an ongoing basis, sometimes many times a day or even every few minutes. Path to production, very critical hygiene factor almost, I would say, almost like the data foundation. Have that capability. The next question, which is a little bit related to the previous one, data science models typically aren't stable. That means you deploy them in production and they start drifting. Customer behavior, for instance, when it comes to meal consumption, can shift. What's popular today, maybe red meat, maybe it's not popular in a couple of months from now, and the accuracy of your model will decay. So you need to have the capability to continuously monitor these models in terms of accuracy, not just the kind of technical reliability, but is the accuracy actually holding up? And what's that relationship between customer satisfaction and minimization of food wastage? Also, that will change over time, typically. And you need to, if you want to scale these kind of capabilities, if you want to build something where you can really deploy and operate dozens of different data science and AI solutions, you need something where this monitoring and, if required, even retraining in production happens automatically. So you need to actively manage what we call data science or AI lifecycle. We treat these things as products, say we deploy them, but there is a lifecycle management process around them. In some cases, you have to take them out and even rebuild them if the accuracy falls. Doesn't apply to all models, but most models drift. It's not a one-off type of thing like a typical IT solution. You build them, deploy them, and move on to the next one. People need to spend time on the lifecycle management, and it needs to be automated. Otherwise, there is no way to scale this. And then of course, relate this to the comment which sorry, it's the previous slide, which I made earlier. The lifecycle management, of course, it also has as a prerequisite that you have a path to production. Imagine the situation that you have deployed something with the help of IT, of an IT department, IT operations department, to run the solution. After a few weeks, a few months, you figure out you have to rebuild it, might need new features. You go through that whole lengthy process again to rebuilding it and deploying it, which can take many weeks or sometimes months. It's the death of any data science initiative. You need that process automated. Absolutely. It's, again, the path to production which matters here critically. The next challenge then typically that comes up is, data science solutions, AI solutions typically change business processes. That's what they're built for. So something will change after you have the prediction. In our case, it's the catering process. So how do you get this integrated into a business process? You've built a nice model, found a way to build it in production in a stable operational environment provided by the IT department that actually runs in a reliable way. You have your scores that come out for each flight, predicting how much should be uplifted on that flight. How do you actually get this into the catering process? Typically, as an IT system, it needs to be integrated. And then comes the next challenge. These are not modern microservices architectures or something like this, or with nice APIs where you just kind of make an API call and either your model serves through an API, or you can push the data in this way out into an IT system. Very often, these are old legacy systems, monolithic, very difficult to integrate with. This is a complication that has to be understood at the beginning of the project, because it might require quite substantial amount of time from the application development teams to even integrate what your model outputs into a transactional IT system, into a business process automation system. Sometimes it's easy, sometimes a simple kind of dashboards and visualization is sufficient. In most cases, data science and AI solutions need to produce their output into another system for automation purposes. And that can take a long time from experience. Our catering system, for instance, we are just in the process of renewing it now and refreshing it, is very old. It's not straightforward to integrate these kind of things. Yeah. So very often overlooked and very often forgotten in the early planning stages of a data science initiative. And if you don't do this in time, again, might end up in a POC or pilot phase and not go much further with a data science solution, which is not too difficult by itself to build. There's a second part to business process integration. There's a business part. The catering example which I mentioned before, you need to integrate not just with an IT system, in that case, the catering system, CAT 360 as we call it, you need to integrate that with a business process. And then the complication starts. A data scientist will typically just think about, I need to predict with reasonable accuracy how much food is required of each meal type. The real question is, how often is food ordered? We're dealing with a plethora of different caterers around the globe, 140 outstations, many different caterers, each of them with different requirements, different processes. You need to change an entire business process in order to integrate your prediction into that process and actually improve it. And it's not just once, it's actually many times with different caterers. When is food ordered from the caterer? It's ordered a couple of days in advance based on the booking figures that you have. You need to update this in regular intervals, the update, and order more food or maybe less, cancel a little bit of the order, all the way till almost the last minute, because there are last minute upgrades on a flight. So you also still have to cater for buffers in that case, because it doesn't matter how accurate your model is, there can always be last minute upgrades, and in that case, additional food needs to be available. So this is a change management challenge. A business process needs to change, and the effort can be very substantial to get this going. Yeah, so those were, as an overview of, as I said, 7 challenges I've observed. In principle, you could talk about more that exist in order to really get things beyond proof of concept or pilot stage. Data science initiatives. It is far more difficult than actually building the algorithm. And therefore, I've tried to summarize this. The main takeaways for me are, when we train data scientists, there's an enormous amount of focus on data preparation and then the algorithmic part. The things that happen around them, I wouldn't say they're more difficult. Academically, they're probably even simpler in many cases, but they're not very often, data scientists are usually not trained in these things and very often are also not aware, so they underestimate the complexity. And that is one of the reasons, or probably the main reason, I would say in totality, that many of these data science AI initiatives still in a corporate environment fail. That's pretty much what I wanted to talk about. So I started with a little bit of a negative outlook, but not in order to show that there's anything negative about this. The potential is excellent, in particular of recent AI developments. So just want to make sure that I don't create the wrong impression. It's fantastic, but there are many, many pitfalls on the way to getting these things in a scalable way into business operation. And it's critical also that young data scientists learn these things from the start, not just focus on the mathematical algorithmic parts, but also understand the larger corporate context in which these things have to run and have to work. That's pretty much it. Thank you very much.
Thank you, Dr. Dirk, for this insightful presentation. I would just like to take any questions, if anyone would like to ask Dr. Dirk.
Everything's clear? Yeah? Thank you. Thank you, Dr.
Thank you.
Our next keynote speaker is Professor Vasily Palade, Professor of AI and Data Science from Coventry University, UK. Please join me in welcoming Professor Palade.
First, thank you very much for, I want to thank you to the Emirates University and the organizers of this conference for inviting me for this keynote talk. And in particular, I would like to thank my former colleagues. You know, I have here 3-4 colleagues from Coventry University with whom I was honored to spend some time in the past and research, and I have current research with them. Thank you very much. So I entitled the talk today, Remote Sensing and Deep Learning for Farmland and Crop Classification. And it presents the results and the project which we developed over the past 4 years with one PhD student working on that, who just finished the PhD thesis, Dr. Shruti Nair, and in this project, I collaborated with Dr. Sara Sharif-Zadek from the University of Swansea and with Dr. Charlie Hill-Butler from the Center of Agroecology and Water Resilience from Coventry University. And with whom I was trying over the past 5-6 years to develop some research on AI applications, and in particular, computer vision and satellite image processing for agriculture, and drone images as well. But let me start by setting up the context first. Why satellite imagery, and in particular, why AI for agriculture? Because there is not many people who have linked AI and agriculture more than 20 years ago, say. So if you would have told a farmer 20 years ago that you want to use AI and help him in his tasks, then he would have said that you have lost your mind. What happened? What changed in the meantime? So in the past 15 years, there have been some transformational AI technologies that transform the field of AI, and then these technologies have impacted many AI applications, including applications to agriculture. So I would name here the advent of deep learning in 2006, with the seminal paper of Geoffrey Hinton. You know him, he's dubbed the godfather of AI, right? And so in 2006, they proposed they introduced this larger neural network architecture, which was called deep learning, let's say. And then in 2012, we have the AlexNet. It's a famous deep learning architecture, and AlexNet has been shown to classify very well images for a variety of domains, which was known to be a very challenging task, right? So we have this in 2012. And then in 2017, we have transformers, right? We all know transformers from ChatGPT, right? Which stands for nothing else than, pre-trained, generative pre-trained transformers, right? So transformers were applied first for natural language processing, and then they moved to computer vision, and we have vision transformers, and today I will try to show how we can use transformers for processing satellite images for agriculture, right? Okay, so satellite images can be used for uh, monitoring the crop status, the crop health, the soil, and also the irrigation of some certain fields. Yeah, and then we can detect the crop health, and then we can decide, we can optimize the farmers can optimize the application of fertilizers or the water, and then we can maximize the crop health, yeah? And then we can estimate eventually the crop yield and report to the government agencies. So we can also manage land use and soil health for regenerative agriculture, right? We can manage resources like the irrigation resources, right? And we can help in disaster management, both for pre-disaster, so we can inform the farmer if a disaster is happening, and we can also help them to assess the damage after the disaster happened, yeah? Not only to say that satellite images can be used for weather prediction, for checking insurance claims, and also for checking if farmers and other companies respect the environmental standards, right? And why are we doing this? So we, as President Kennedy said, we as humanity, we are in a long war, and probably one of the biggest wars of the humanity, which is the war against hunger. Yeah, so we, according to the United Nations statistics, about 8%, but more in the past. In the previous reports, we had 11%. And to be fair, I believe that we have more than 11%, somewhere between 10 and 15% of undernourished people in the world, especially in the low-income countries, but it happens also in the developed countries. A lot of people don't have enough food on their table, even in the developed countries, right, these days. And not only that, but the population is increasing, and will soon be 10 billion. And then we have to match that demand. And to give you another quote, famous quote, which I don't know who said it, but probably is anonymous. There is no greater and deeper love for a man than the love for food, right? And we are all guilty of that. Yeah, let's be honest. We are all guilty of that. So even in as the society develops, then we try to eat more food, and then there is a lot of waste as well. Yeah. So we have to match that demand. Yeah. So if we look to that graph on the right, you'll see that the total factor productivity is increasing at 1.5%, and we need to be at 1.75% to match with that demand by 2050. Yeah. So we have to do, and satellite imagery and the AI can help, can address these challenges by developing scalable satellite and AI-based methods to monitor farmland and classify crops and eventually predict and maximize crop yields. Yeah. So all these issues will to United Nations Sustainable Development goals, which are SDG 2, life. Zero hunger, and SDG 15, life on land. Yeah. So agriculture relies on field surveys, and if you do it manually, it's very expensive and it takes a lot of time. So that's why we are trying to use satellite images to have these field surveys. From up there, we try to see what is the status of the crops, the status of the soil, and so on and so forth, right? And there is good accessibility, because if we use data from NASA satellites or European satellites, they are free, and then we can use those data free. If we want to have greater resolution images, we will have to pay more money some money to private companies, right? So there is great coverage, yeah. So it scales over large areas, and it's cost effective, yeah. So if you are happy with free images from NASA satellites or European satellites, then you don't have to pay anything, just use those images. If you want greater resolutions, then you'll have to pay some private companies to get more, to get better images, right? Also, there is regular data collections, which allows continuous monitoring. All these satellites will circle the Earth with some periodicity from, 1 day to, 15 to 16 days or something like that. Yeah, so there are several famous satellites, yeah, which can be used, yeah, which provides data to be used for agriculture. The most famous one is the NASA Landsat missions, which was launched in 1970s, 1972, and there was several missions, Landsat 5, 6, 7, and the 8, yeah? So initially the resolution was 30 meters. So if one pixel in a satellite image would have covered an area of 30 by 30 meters, yeah? You will need higher resolution, and European Union has launched the Sentinel-1 and Sentinel-2 missions, which has a resolution of 10 meters. So each pixel in a satellite image will cover a 10 by 10 meters, yeah, resolution. And then the revisiting period is 5 days as compared with 15 days for Landsat missions. Then there are many other countries have developed satellite missions. France has SPOT, Germany has TerraSAR, China has, Brazil has, and all major economies will have some satellite missions like that. And then, in addition to that, we have private companies who want to get a lot of money from satellite imagery, right? And one of them is Planet, which launched in 2018, about 200 microsatellites, and then they have a resolution of 3.5 meters. So there is greater resolution, and also the revisiting period is 1 day. So if you want to monitor a crop, then you can do it better with this kind of images, which provide greater resolution and then taken at more frequent interval. But there are some key challenges in using satellite images for crop detection. One is that many crops, if we want to, from up there, to detect different crops, like classify wheat from maize, then they may look exactly the same from up there. So crops may look alike at certain growth stages, in different times. Then the resolution is very important, In a 30 by 30 square meter, if you use the Landsat resolution, you can have a lot of things there. You can have a building, or you have something else, right? Then there is temporal variability, Wheat crop in early stages doesn't look the same as in late stages, right? But the biggest problem of all is label scarcity. So in order to develop models, deep learning models, we need label data, right? So deep learning models, as known by everybody, they are hungry of data. We need a lot of data to properly train well. And then we don't have label data. Because if you have a satellite image with a lot of pixels there, 30 by 30 meters, someone would have need to spend some time to label each pixel, farm, non-farm, or wheat, maize, orchard, and so on and so forth, right? So we don't have this type of labels. This is the biggest problem encountered in satellite image processing. And then another problem is field boundaries, So if you have countries like with very small farms, then you will not be able to detect what they have there on their farms, And then, because simply, it's not possible to distinguish at that level of resolution, right? So this was our problem, and I will explain a little bit later. Because when we started the project, because the project was founded by the Global Challenging Research Fund, we had to look for some application to low-income countries, and we started to look at some countries from Africa, Nigeria, and Ghana, but we didn't have enough coverage from satellites for those countries, and this was the first issue. And the second issue was that we couldn't distinguish what the crops are there, because the farms were very small, and also the vegetation was very different. So we had to move from a more familiar region, which is Europe or United States. Right, so I'm just starting my talk now. So the main aim of this project is to develop novel deep learning methods for scalable crop monitoring under label and domain scarcity. Hope you understood, right? And we have three main goals, which are there. First, we want to address the problem of label scarcity, So we don't have enough labels. So for that, we want to solve this problem. We don't have enough people to label a lot of satellite images to be able to properly train the deep learning models. So one was to use different methods, machine learning methods, to come up with more images, artificial images, right? And we use generative adversarial networks. We'll talk about that later. Then we'll use some transformer-based methods. I told you about transformers, yeah, that learns domain invariant spectral embeddings, yeah, from multi-temporal satellite imagery, yeah, yeah, for crop detection. And then we'll use another method, which is a teacher, multi-teacher based method, source-free and semi-supervised learning method. We'll talk about these three very shortly in turn, yeah? I will not go too much into details. If someone is interested, please ask me for details later, and then I will provide also the publications. First, let's talk about, the project started like that. We wanted to estimate the yield. So just for looking from up there, we want to estimate how much yield you have for a certain area, for example, northern Italy. Yeah? For that, you have to detect the farms first, where the farms are. Then you have to detect the crops, which is more difficult. Yeah? So if farms are difficult to detect, because you don't know where the boundary is, if it's a farm, it's a non-farm, and something like that, then it's more difficult to detect what type of crop is there. And then to estimate, given the vegetation, how the vegetation looks like, to estimate the yield. And then having some historical time series in the past from the government, then to predict how much the yield is this year. But that was too ambitious, and then we had to limit ourselves to one problem, which was segmentation, detecting the farm lands. Yeah? So you have, if I give you a satellite image, how to tell me where the farm is, to delineate the farms, yeah, from non-farm areas. That is called segmentation in general in computer vision, right? So let's say this is what we have there. So the area we focused on was northern Italy. Why? Because there is enough coverage from satellites and the farms are bigger. And then they usually put their corn and maize, yeah, corn and wheat, yeah. Italians like a lot of pizza, so they have to have wheat. So, this is what you have from the satellite image there on the right side. You'll have, yeah, this is how you'll have some tiles. You know, the satellite image will come in some tiles which covers about, now, several hundreds of kilometers, right? And from that tile, yeah, so this is the satellite, the RGB, yeah, image, yeah, in the visible range. Then we, for learning purposes, we divide that image in 256 by 256 pixels, yeah? And this is, yeah, here is the labeled mask, yeah? With white is the farms, with black we have non-farm areas, yeah? Again, we didn't have labels. We have the satellite images, and the first task was to create a data set, a labeled data set. So we had to do for each of the pixels, yeah, looking in Earth Explorer to indicate farm, non-farm. And then it was a very laborious work to create about 200 images like that, 256 by 256 patches, you know, with labels. Yeah? This was the first task. Yeah? So the first task was to label into farm, non-farm, for those images we have from northern Italy, then to see, okay, what kind of deep learning method we can use. There were many, in the meantime, many deep learning models that some are good, some are not good, you know, and which method can be appropriate for processing this type of satellite images. And then we investigated two frameworks, UNet and DeepLab version 3, yeah? And just to see how well it can process these satellite images. And then the next task was to process what kind of, what are the inputs to this model, what kind of, I didn't explain you earlier here in this image, so I forgot to tell you. So this is what you have, for example, this is a time series for a wheat farm in France, yeah? This is what you get from the satellite. You have 13 bands, yeah? So the satellite will get the reflectance value in 13 bands. Some are visible bands, red, green, blue, right? Others are non-visible, near infrared or shortwave infrared, and so on and so forth. Yeah? So we have the 13 across a year. You know, we have the days of the year, 0 to 300 and something. And this is what a field of wheat will reflect in those days in the 13 bands. And we use this as an input to predict, yeah? Good. Let's go further. I forgot when I started, but I think I do have 10 more minutes, right? So, one problem we have to solve was that we don't have enough labels, right? So we try to label 200 images, yeah? It's a lot of work. Then why not to create artificial images similar to those images? So using some methods. So this is another task in the first part of the project, right? So, and then, as I told you, we investigated 2 frameworks, deep learning frameworks, UNet and DeepLab version 3, using transfer learning, yeah? So rather than starting the training from scratch, we use some models trained on other types of images, and then we just fine-tune with the satellite images in order to get what we want, yeah, to segment between farms and non-farms, yeah? And we use popular models like VGGC. People who work in this area, they know this, yeah? VGG16, ResNet 50, ResNet 101, Mobile Net 101. Some are developed some of these models are developed, like inception models are developed here in the UAE, right? So we use some of these models, and then in combination with the frameworks UNet and DeepLab v3, and then this is the segmentation result, yeah? So, for example, for UNet here, this is the original image, this is the mask, yeah, the real mask. White is farm, black is non-farm. And this is the result of segmentation using the 4 transfer models, yeah? So we use this pre-trained model, just fine-tuned, and then we obtain those results, yeah? So this was the first task. Another investigation was how to use all the 13 bands in a better way to do your job, which is segmentation, classify pixels between farm and non-farm, yeah? And you can use directly all the 13 bands, or you can come up with some measures, which, you know, one of the measures to detect vegetation is called the normalized difference vegetation index, yeah? So if you look to this formula here, so if we subtract from the near infrared band, the red band, and divide by the near infrared plus the red band, so this index here will distinguish between vegetation, pixels with vegetations and pixels without vegetations, yeah? So we try to use NDVI, which is a popular measure in satellite image processing. And we tried various other combinations, for example, shortwave infrared in combination with near infrared bands, which are good for discriminating between different crop types and the soil, yeah, the pixels with soil, and then they can distinguish between different types of crop, soil, and moisture combinations, right? And this is the result, what you have there in at the bottom there, results of training and testing accuracy using UNet, yeah? Using different band combinations. So the next method is using generative adversarial networks to generate more artificial data, because we don't have enough data, and then we need a lot of people to label those images, right? So, and generative adversarial network is another technology which was proposed in 2014, yeah, to create more images, more artificial data. What is the problem? So in this method, you have 2 types of networks. One is the generator, which create the images, yeah, more images like the real images, so more artificial images like the real images, and then you have a discriminator, which will do what? We'll try to classify those images into real or artificial image, or fake images, yeah? They have contradictory goals, and they are trained together. In the end, you will be able, with these generative adversarial networks, you will be able to produce better artificial images which are similar somehow with the real images, yeah? We use a particular type of GAN, which is called conditional GAN. It has been applied before for medical image processing, but we modified it for satellite image processing to create more artificial images, yeah? And this is what we have here. Good, and then we added the new images to the data set, and then if you have 200 images and if you add another 2,000 created artificially, it doesn't look good, right? So we investigated how many artificial images you can add in order to do a good job, yeah? And then we decided that about 40 artificial images is the right number to add to the real labeled images to do the job, yeah? The second part of the project was to, do I have 5 more minutes? 5 more minutes, yeah. Was to detect, now, let's say you have you don't have a lot of, the main problem is that you don't have a lot of images, yeah? So the second problem is how to classify crops. If you didn't have enough labeled images for farms, now you'll have many more images to detect, label images to detect crops, because there are a lot of crops, wheat, maize, orchards, and so on and so forth, right? And the idea is how to use label images in one country, for example, Denmark or France, how to use those labels in a different country, which is called domain adaptation, yeah? So let's say you have some data, labeled data in France, Denmark, and Austria, and you want to use those data to train something in Italy, which is called domain adaptation, yeah? You have a problem. You have many problems, in fact, yeah? One problem is that the crops don't look the same in Denmark and in Italy, yeah? So they grow in different times, yeah? So you have to account for that. And we have two problems here. We have the data, original data from Denmark, and also when we don't have the data from Denmark, yeah? So the first, so the 3 countries, source countries are France, Denmark, Austria, and then we want to train some model for Italy, yeah? Where we have a limited number of images, yeah? And then we used a transformer-based, transformer, that is the structure on the right side. Don't be scared about that. If you want some details, we can talk later. Yeah, and then we, using data from France, Denmark, and Italy, we were able to develop a model for Italy where we have a small number of labels. So we have a few labels from Italy, and then we use the models from France, the data from France, Denmark, and Austria to develop the model for Italy. And then we have the results there. As expected, France, because it's closer to Italy, you know, it has a better influence on developing the model, yeah? So this was the first method. Then the last approach was a multi-teacher learning strategy. So let's say now that you don't have the data from Denmark, France, and Italy, yeah? But you have the model. Someone developed the model in France to detect some crops, wheat and maize in France. Someone detected the model for Denmark. Someone detected the model from Austria. And you want to use those models only. You don't have the original data. But you have some small data, a little bit of data from Italy labeled, and a lot of unlabeled data, yeah? So this is the idea. So you want to use 3 teachers, teacher model, to train a student, the Italy model, yeah? Yeah? And this is the idea of a multi-teacher learning strategy, where you have the original models from 3 original source countries, and then you have a little bit of labeled data from Italy, but a lot of unlabeled data. This is the whole idea. This is the framework. I don't want, because I'm out of time, don't want to take much of your time. So if someone is interested, this is the model which is published in the paper shown there at the bottom. And then I will end with some future directions. So what I presented in this talk was basically how to use satellite images to detect farms and crops, yeah, but satellite images at medium resolution, 15, 30 meters, yeah, 10, 30 meters. So the challenge is it's better to have better resolution, yeah, let's say, and higher frequency, but then not all problems are free, because you'll have a lot of data, and then you'll have a lot of other challenges, you know, the models will be overtrained. Then, another idea to extend this is to use human in the loop and active learning, yeah? So if you have some pixels inside the farm, it's very easy to classify, it's in the middle of the wheat land, yeah? But if it's at the border, you know, there may be a road, there may be a building there, yeah? So we can ask people to label only those problematic pixels, which is called, in an active learning method, Also to use data from multiple satellites at multiple resolution and so on and so forth, Incorporate additional environmental data, can help in predicting better, right? And then, in the end, we still wish to obtain an end-to-end yield prediction, So if we look from up there to predict how much you will get from that piece of land, how much wheat you will get, but it's a challenging problem. This is the list of publications, if someone is interested, and thank you very much, indeed. Yes.
Thank you so much. This was fascinating. Your goal at the end of the day is to predict yield, and I wonder if instead of monitoring if the wheat is tall or short or blooming, is it enough to just monitor the farmer's bank account, how much they're selling?
No, is it enough? Can you repeat? I didn't hear.
I wonder if you could train your algorithm not necessarily monitoring the ground truth of what the wheat is doing, is it blooming, is it tall,
Yes.
short, but monitoring the farmer's bank account, how much have they sold as the ground truth?
No, we tried, the original idea was to have data from the past. For example, you have the satellite images from 10 years ago, from 5 years ago, from 1 year ago, right? And you know the yields 10 years ago, 5 years ago, 1 year ago. You have the satellite images now, predict what's happening this year, right? This is the idea. We haven't looked at how much they have sold. We can look, not sure if there is data enough, how much they have sold, but there is data how much they produced, how much the yield was on different farms, in the past. The government has, especially, that's why we looked at Italy. It's a difficult problem. Finally, we had to scale down. It's still enough, it's still challenging to predict farms and crops. Okay?
Thank you, Professor.
Thank you.
Thank you very much.
Thank you.
Our next keynote speaker is Ala Radwan, Lab Lead at Sensible City Dubai, part of the MIT Sensible City Lab. Please help me welcome Mrs. Ala Radwan.
Hello, assalamu alaikum, good morning. Bear with us until we get part of the good. Perfect. Thank you. Thank you, EAU, for the invitation. I'm going to try to make this short. I'm going to run through everything because we have 20 minutes and I really do need to get out of here. So we're going to change the scale up a little bit because we're going to be talking about cities and specifically how we can make our cities more resilient and design smarter cities for the future. So if anyone has not heard of this little institution in Cambridge, it's MIT. The Sensible City Lab falls within the Urban Planning and Architecture Department. And we were actually established 20 years ago. So we're a very old lab, one of the first in the institution. And we're made of 60 researchers globally. And what makes us very strong in what we do is that we're a very multidisciplinary team. So we actually have architects and mathematicians, data scientists, all coming together to talk about how we can design cities that are smarter to make sure that we're addressing the issues that we're facing today. The way that we do this is two ways. One, we analyze a lot of data, as much data as we possibly can. And when data is not available, we do a lot of collecting data of our own and designing our own sensing platforms. So you could see me in the center in the bottom. We're deploying robots in Cambridge, Massachusetts to look at the health of the city. Just a little example. And we work with cities all around the world, and more recently, we've been very lucky to establish labs. So of course, we have our main lab at MIT, but now we have 4 global labs across the world. We have one in Amsterdam, we have one in Rio, so it's the black dots. I see people counting. So it's in Rio, we have Seoul coming in January, and in Dubai, established with the Dubai Future Foundation 2023, which is where I'm based. So let's talk about the problem. We're all very knowledgeable in the fact that the world is getting hotter. A lot of us has felt this personally. It's getting so hot that they predict Paris is going to be at 50 degrees in the next 20 years, which of course this is something that we as someone who lives in this region know very, very well, but also positions Dubai to be the forthcomer in addressing these issues early on and then be used as an example for cities in Europe. Unfortunately, the way that we address this warming is using ACs. Hopefully we're not using units that are this old, but actually people all around the world are adopting this. And what we don't realize is that when we cool our indoor spaces, we actually dump all the hot air out into our outdoor spaces, making our cities more unlivable. And so we have another approach, and it's not novel. Everyone knows greenery is great as impacting and reducing temperature, but we wanted to do a couple of things to really quantify that effect. And first, we wanted to understand where trees are, and if anyone knows how tree data is collected. So there's a single person that goes around tree, and inputs the data, or they use satellite images. Right? And so although these are very accurate methods, they're not very scalable, and they're also not very open source. So what we tried to do, we're going to just make sure we can hear, is that we use AI and Street View images as the very simple method to understand what greenery exists in a city. And so what we came up with, and we actually did this 10 years ago, so this is something that we've done a long time ago. We come up with this value that we call a green view index. And what it tells us is that we understand where our trees are, what species are in the cities, and we've been able to do it for cities all around the world. And of course, all of our data is open source, so anyone who wants to use this data for their own research are able to access it through our websites. And so now that we understand where the trees are, we actually want to give a tree a quantifying element to it. And so what we did is we did our own data collection here in Dubai, and we collected 3 points. We collected thermal images, we collected RGB images, and a temperature reading using a Kestrel device. And we didn't only do this for one tree, and I'm saying this because I was part of the data collection team, and we did it in Ramadan when we were fasting. It was exhausting, but we did 30 trees per one site, 5 sites, 3 times a day. And for us, it was very important to understand kind of across the day how the temperature changes. And what we could and what we did find is that when you take an empty site, and you can see one that we took in Dera, and then you add a magnolia tree and you simulate the cooling effect that we were able to record, you have a change in perceived of temperature. So instead of 27.5 degrees, which is the base, you actually feel 23.7, and a fig tree even does a better job, and the perceived temperature becomes 19.4. And so we know a tree is a natural cooling system, so maybe we could cut down on the usage of ACs. But we also wanted to understand, so we understand trees, they cool, but what species does a better job? And through what life cycle of a tree can you actually look at the transpiration rate? We look at the temperature of the crown of the tree, and we created these simulations that you can also see here in a quick video. And we started actually with mapping out all of the trees in Dubai first, because if anyone has worked in Dubai long enough, this data is not available to all of us. So we started with mapping it in density. And so we created this model that shows actually the areas that are more dense in greenery versus other ones, and then we even took it to the species level. So within that one 500 meter by 500 square, you can actually see what species are in there and what their cooling effect is, what their transpiration effect is, and actually what components within a tree and the tree architecture has the effect. And this has been published, so you could see this, and please do a deeper dive into all of what we have been able to come up with as a result. And then we're going to look at a different problem, and this is air quality and using as a proxy for climate change. And so we know that cities are getting, we also experienced this a couple weeks ago here in Dubai, where the air quality was incredibly high. And so the way that cities monitor this is by using a standing air quality monitor. which is great. It's absolutely something that is accurate in the data that it collects within the radius that it is placed in. But we know from research that actually even one segment of street has a different air quality reading. So we decided that we wanted to design a mobile air quality sensor. And instead of introducing newer vehicles into the streets, we were like, could we use urban fleets? So could we use something like a trash truck, which is already a vehicle that is going around the city many times during the day and the week, and can we actually create a sensing platform that can read air quality using this? And so we designed our first city scanner. Can you hear the volume of the music? No, good. Okay. And we turned trash trucks in the city of Cambridge to these sensing platforms. And this is just the first prototype that you're seeing. I'll show you what it looks like today. So we're looking at humidity, we're looking at temperature, we're looking at air quality. And so what we were able to create out of this is an interactive map that you could even access. And if you were wanting or curious about what the air quality looks like at your work or at your house, you're able to get it to that point of detail where you know what you're experiencing and what even you're breathing in. And so this was our first prototype, and of course it's very low tech, and it was just, as researchers, we do a lot of prototypes. And we had a big problem that the fixation method of this was very hard to add into or onto vehicles. So we moved into this device, which is called flat burn, that actually magnetized onto vehicles and still has the same reading, and also is self-sustaining because it has a solar panel, so it operates on its own. And of course, as MIT and the research that we do, we make everything open source. So even you today, or even your students or whoever wants to explore, and you could 3D print it yourself. We also have videos on how you can do it, and we've even tested it in workshops across the world to make sure that it's user-friendly, at least maker-friendly, where you're able to design this own device. And we've actually deployed this in many cities around the world in different applications. So yes, it kind of reads the same thing, but we did it in Canada, in mining cities, to understand the impacts of when you do have a mining city, what that does to air quality. We actually even deployed it in Rome, but more looking from the thermal image aspects to assess the health of trees and many, many, many other different applications. And still to this day, we actually brought it to Dubai to try to test air quality and just a couple of readings, and it melted. And that was, I will say, the first time it's ever happened to us, where it melted on top of my vehicle and stopped working. So now we're doing a different iteration that maybe works for our climates. And then I'm going to move on to the last project. And so this one really is looking at alternative modes of transportation, because with air quality comes, of course, from mobility, has a high impact on that. And so the city of Amsterdam was facing this issue, and they came to us with one request. They're like, we're trying to address traffic, we're trying to address air quality. We would like to design an autonomous car. But if you look at Amsterdam and the city of canals, right? So if anyone's been there, there's actually more waterways than there are streetways in some of the areas. So instead of designing an autonomous car, we said, what if we design an autonomous boat? Like, could we actually add to the existing transportation infrastructure and design an autonomous boat that can have many different applications? One, of course, it can transfer and transport people around the city, but we've also done many different things with it. The first problem is that if anyone has seen what a summer day in Amsterdam looks like, you have like one person trying to navigate through traffic. It's actually very complicated, especially when you're trying to design like a self-navigating boat. And then you also don't want it to be just a boat. You want it to have different applications. You want it to maybe, possibly, does it transport, can it be like Amazon? Does it transport parcels across the street? Do we design a fleet, and do they come together and build bridges that can kind of increase connectivity in certain areas of the cities? And so we went back to MIT and we started our prototyping, and of course we did it at a very small scale first. We also tested it in our MIT pool. This should play, and I really would like it to play. Yes. So because at MIT we don't really use our pools for swimming, we use them for robots. And in some cases, when we're trying to test technology, we send our researchers to be the obstacles. So you'll see one of the researchers like walking across, and he is the obstacle, and the boat just still manages to move around him. And so 10 years later, because it takes a very long time to do this, this is rowboats.
Is a rowboat, a fully autonomous, zero-emission boat that operates on urban waterways, and she can change the way cities work. As congestion and emissions continue to rise, while cities continue to grow, the existing infrastructure of many cities struggles to keep up. Rowboats offer a solution by moving road traffic to the water. By bringing passengers from A to B, or as an on-demand boat, taking you anywhere you want. And they can also help the city as a multi-purpose workboat. Take Crystal. She is equipped to collect household waste to free the streets from heavy garbage trucks. Rowboats are fully autonomous, so they navigate without a skipper and can operate 24/7. In order to sail by themselves, rowboats need to perceive their environment and recognize objects such as bridge pillars, floating objects, and of course other vessels. The primary source of information comes from a LiDAR sensor, but rowboats are also equipped with cameras, GPS, and a digital compass. Rowboat's onboard computer combines and processes all of the data and runs the rowboat software so it can successfully complete its mission plan. After 5 years of development, testing, and experimentation, we have now successfully enabled autonomy on the full-scale prototypes. Rowboat is ready for the next step. Join us and let's unlock the potential of...
That's all for me today. But I will say the final thing is that Rowboat was one of the projects that took a very long time. They said 5 years in the video. Actually, it was closer to 8. But actually spun into a startup. And now if you're in Amsterdam, you can actually ride the boat and you can actually see it and just actually experience. But this is just a translation of how research can actually be turned into an applied either product or even a way that we could design our cities. That's it for me. That's all.
Thank you, Angela, for this inspiring presentation.
Of course.
Anybody would like to ask any question? We have a few minutes.
Yes, one.
I may have missed it, but it looked like for your tree program, it was based a lot on direct collection in situ, and I wondered if you're able to get widespread of data from satellites, or you really need that granular on the ground level of data?
Yes, so we did try, and we still do use satellite images, of course, and we'll talk about this later. We do use it a lot, but there is a depth that you lose, especially when you're looking at things like shade, tree height, tree density, that you can't necessarily get from just a satellite image. But we did also take our research further and not just look at it from even the street view perspective or like an image. We also, and this also you spoke about, we're looking at how we could identify and label trees that are actually species just by using an image. And it's very, very difficult and challenging to do because it's so hard to identify a species from another one just by using AI or a model. But satellite is great. Sometimes it just has its limitations. Yeah.
We have another question.
So like during your research, did you observe any like herding effect? Like, for example, if there are a lot of trees in one region, like overall how many degrees Celsius will that
Yes.
region reduce?
So we've been able to look across all of Dubai, and we have a big range. So it can be anywhere because it's something that's very perceived, right? So what we say and the way that we quantify it is like any change in temperature or perceived temperature from -2 degrees, so actually some trees are awful at actually cooling, to 10 degrees. Yeah.
Thank you.
Yeah, of course. Which I will say, although the palm tree is beautiful, it is awful at cooling. Like I know it's a cultural, cultural tree for us, and it's beautiful. We should continue to grow it, but if you're trying to cool certain areas of the city, that's not the one. We actually found the neem tree and the raf tree to have the highest reduction in temperature. But you could also, our publications are all public. Please read it, and then contact me if you have any other questions.
Right. First of all, thank you for that very interesting presentation. My question is, and apologies if I missed it, so you have a number of sensor systems that are collecting data, and you have created a digital shadow that monitors that data. Does it have any adaptive capability? Does it update itself with new data? Does it retrain when new data becomes available? What happens then?
Yeah, so it
Thanks.
really depends. So most of our sensing devices have gone into kind of like adaptation in different prototypes. And that's just because of how we're learning when we use them. Some of them have been actually taken and like a startup has been created, and then it's a completely different application and even a completely different product, I guess it would be a product at that point. But we do, of course, in research, it's an iterative process. So we're continually adapting even the technology that we're using. Even right now, the robot that you saw, it still operates, even though it is autonomous, it operates with a captain. So there's always like a captain. Now they're trying to design a chip that acts as a captain. So they're having to readapt some of the technologies because we've come so far to where it could be with no driver or no captain that has to like steer the boat or even just kind of help in the navigation or monitoring, and it can be and will have a chip that is actually even called captain. Yeah, of course. Thanks. Thank you.
Our final keynote speaker for this session is Ms. Alia Al-Mazroui, Director of Research and Weather Enhancement Department at the National Center of Meteorology. Please welcome Ms. Alia.
So, hello everybody. Good morning to everyone. I'll be speaking in another field, which is going into water, looking into the water, food, energy nexus. And as you know, the most critical challenge we have nowadays is the water security challenges. And here we'll be speaking about finding solutions through the cloud seeding or rain enhancement, I can say. So as the director of the UAE Research Program for Enhancement Science, UAE, I'm honored to share our journey of groundbreaking, transformative solutions in the field of cloud seeding. For nearly a decade, this program has been at the forefront of transformative research across a range of scientific and technological domains, including cloud microphysics, seeding materials, delivery systems, looking at numerical modeling and forecasting, and as well AI-driven techniques for precipitation enhancement. And by presenting the research in this conference, I would like to guide you through the strategic journey, highlighting the UAE's pioneering contributions and achievements toward building a climate resilience and sustainable future for today. So, looking at, since I spoke about the importance of the water security challenge and looking at it from a global context, the UN predicts that almost half of the world's population will face high water stress by 2030. The efforts today to address water scarcity are insufficient to prevent dire consequences, and the water scarcity lacks the public focus and funding it deserves, I can say, till today. Escalating the water scarcity worsens existing global threats like climate change and arid and semi-arid regions like the UAE is particularly here vulnerable. So if we look at the UAE climate and why we are really considering this thing, and we're putting a lot of efforts and support as a country to this field, the UAE considers the water security as a strategic national priority. Due to its dry climate, the annual rainfall, the very low annual rainfall that estimates less than 100 millimeter, around 70s, a very high evaporation rate, and a low groundwater recharge. And if we look at the rainfall enhancements from the lens of weather modification, as it's part of this bigger field, we can find the significant benefits and the importance of rain enhancement here, which I can mention as the first, reducing the need for the desalination water or the desalination technique. And of course, this lowers the energy use and fewer carbon emissions as well. Again, it supports the rain-fed agriculture, minimizing the groundwater depletion and desalinated water use in this, lowering, of course, the agriculture carbon footprint. Another importance also that it restores desert ecosystems, fostering biodiversity by creating wildlife habitats. Rainfall enhancement also provides insights into atmospheric processes. This is relevant to forecasting and understanding extreme weather phenomena, supporting improved disaster preparedness for the future in arid and semi-arid regions. And through studies in the last years, it has been shown that it provides an economically viable, cost-effective mean and environmentally friendly mean of providing fresh water through rain. If we look at the timeline of the rain enhancement, the first attempt in the country was 1982. I don't think a lot of people know that here in the country, since it's not really aware from the public. But it was started as a first attempt to try to look at the potential of this technique in the country, it will work or no. Starting with a lot of studies at the beginning in collaboration with ANCAR, NASA, lots of universities. It shows a lot of potential. There is a lot of studies looking into what are the materials needed, what are the methodologies, what is the methodology which works here in the country. And from that day till today, we have a strong infrastructure now in the country that enables us to conduct 24/7 operations in an efficient way. And till today, we can say, and of course, in the timeline of these achievements, we've launched 10 years ago a research program to support all of the efforts done in this field and to push, and it was an international research initiative pushing the scientists and researchers around the world to look more into this field, to add value to it, and to push the boundary of the science, coming out with state-of-the-art techniques. This is all to enhance the efficiency and the deployment of techniques in this field as a viable technique. So when we look at the program components here in the country, operations, manufacturing, and research, for the operations, as I mentioned, 24/7 operations here, done locally here in the country and upon some directions also outside the country, supporting lots of countries in Africa and Asia so far, and we're still continuing to do that for the last 3 years in the country. Manufacturing, we do have also the factory that supports our operations locally and regionally, and this is through producing the needed seeding agents that we use in our operations. And for the research, as I mentioned, the UA-ERP program is supporting here and making sure here to cover as much as we can research gaps internationally in this specific and niche field. So when we look at the operations in numbers, we do have 4 aircrafts, King Air aircraft, C-90 GTI. The number of missions differs between 300 to 350 annually, and the flight hours per operation is 3 hours. Now, within the studies we have, it shows a 25% enhancement on rain, whenever we boost the rainfall through the operations. Now, a very important information to know is we do interfere for that when we have, and we add this 25% when there is a need to boost that. So when we have the clouds or the convective clouds that we can really boost, and again, when we do not have any extreme events that you don't really need to go to this line of booster. For the manufacturing, as I mentioned, it is established 2016. This helps us to produce different types of flares here in the country. The hygroscopic flares for aircrafts and for the ground generators as well, and the novel nanomaterial flares, which is the novel material is one of the breakthrough outcomes that came out from the program the last 8 years, or 9 years from the program. So I can say that now we are pioneering or the exclusive global producer of this material in the country, and it received a very high interest in the scientific community worldwide. Looking into the research, and this is the important part of this whole program, feeding both manufacturing and operations and enhancing the effectiveness of both. So this is an international initiative came from the UAE globally to the other countries, pushing and supporting the scientists, researchers from different areas as well, and from different fields to make sure they add value to this niche field. So it can be in another field, but it's also adding value in this niche field, as we have some of our projects working on it. It offers grants, research grants, like up to $1.5 million for each project. But the most important thing here that we are inviting different categories. And the most important thing is that we are always pushing for the international collaboration between institutions, countries, and the same project. This is to make sure that we push for implementation and deployment, not standing only for publications and research. So our vision to become the globally recognized model for rainfall enhancement research, development, demonstration, and deployment of technologies, and the mission for that is to establish scientifically validated technology, platforms, and techniques that contribute to enhance rainfall. Our approach to deliver this and our strategy is to enhance the level of research and innovation in the field, advancing the scientific understanding of this niche field, again, advancing the state-of-the-art techniques, and most important part is also enhancing and further developing the capacity in the field locally, regionally, and internationally, grabbing the attention of the new generation to come and to add more value to this niche field, I can say. When we look at the technological infrastructure we have nowadays, so the UAE Arab leverages advanced infrastructure to support research and operational deployment. We have the atmospheric HPC system enables real-time, high-resolution simulations and AI-driven analysis with 2.8 petaflops of processing power and vast storage capacity. And this is in the National Center of Meteorology. Of course, we are also working with researchers and other universities, so using more high computing systems as well from different entities. All modeling results, parameterization schemes, and data from the projects of the program, including aerial, ground-based field campaigns, are compiled and integrated on the NCM's HPC. And this allows for consistent testing and refinement across projects. Of course, a decision tree-based algorithm also was developed to guide cloud seeding operations. This achieved up to 67% alignment with actual seeding decisions. Taking this infrastructure into consideration, you can see now the cloud, this diagram. It shows a conceptual diagram of a convective cloud with the boundary layer and the intended research intervention area for each of our 14 UAE Arab projects so far. It ranges You can find how it ranges in areas from land cover modification, research, aircraft, airborne campaigns, to novel seeding material development and testing, as well as new laser technology platforms. And of course, this includes a lot of information, a lot of progress reports, which are all accessible through our website. Even the papers are all accessible through this website. I do recommend you to visit and to look more into each of these projects, the different projects. And of course, 4 of them are more into the AI or machine learning applications within the project. I can say that artificial intelligence and machine learning are central to the UAE Arab projects and vision. Out of the 14 projects awarded to date, 4 have strategically integrated machine learning, AI, to transform forecasting and operational capabilities. I can mention 4 of these projects, which are very important projects, in collaboration with the Finnish Meteorological Institute under Professor Halil Korhonen. We have a project of applied AI models to identify seedable clouds, laying the foundation of operational seeding forecasting tools. Another project also in collaboration with the University of Colorado Boulder. It's in developed UAV algorithms and autonomous seeding prototypes, later transferred to NCM and advanced with Khalifa University so far. So it's now in an applied research project, again, with Khalifa University to look further development into these UAVs. Another project is with Professor Luca Monash from Scripps Institute. It's built machine learning-based nowcasting tools delivering 6-hour forecasts. Now it's integrating to the NCM's radar systems. And the 4th project is with Professor Daniel Rosenfield in collaboration also with MBZ UAI, designing an AI decision support tool for real-time cloud seeding operations, currently under its a midterm evaluation of the operational adoption. So these initiatives demonstrates how AI technologies are reshaping weather modifications today. It's a very important driven techniques that adds a lot to this field and still needs a lot in terms of research and testing around it. Looking into the milestones so far, I can say that the UAE became a key platform for rain enhancement research today. As part of its global efforts in weather modification and as part of its multi-efforts toward securing or toward the water security strategy. We've led the first ever town hall meeting on rain enhancement during EGU 2019. What makes this very important thing and as a milestone, it reshaped the potential research areas that we target. And accordingly, it has been also added to the studies that is done by the WMO and the analysis, the peer review analysis of the rain enhancement field today, internationally. We introduced innovations in rain enhancement such as AI and nanotechnologies. The nanotechnology was first time deployed in this field through the new material. We've also featured on the National Advanced Science Agenda of the country, 2031, and received the UAE's Future Fit seal because of the focus on the technology readiness level and how we look at it as an important thing to reach. We do not, when we look at the 1 till 9 technology readiness levels, we always aim to reach to the commercialization phase, which is 9, whenever we can do that. And this is with one of the projects, we do reach the commercialization, and nowadays we are producing the material that is developed and assessed during the last years. And of course, we empowered the youth to actively participate in that, and this is very important in this field. There was very important need to look at, to have a proper outreach, to reach out to the right stakeholders, not only the scientists and the researchers around the world. The most important part of that is that we are here acting as a platform So there was a very high need to connect the scientific community, the scientists and researchers, with different categories, the policymakers, the private government sectors. So looking at the multidisciplinary collaboration here was very important, and here was the importance of the outreach plan. So far, more than 76 countries involved with 3,700 stakeholders, 8,800 researchers engaged so far. The fund given in this program was around 22.5 million, and we still look at it in a very long strategy commitment. So we are committed to also support additional projects within the coming years. If we look at the scientific contributions so far, it's 105 scientific articles in this specific field, 11 obtained and registered patents. The last one was on the laser technology, and more than 150 conference proceedings just in these 14 projects. One of the most important question we've always asked is that what's the economical value out of what we are doing? And since we have the desalination and it's a solution here in the country, so why you're looking to another solution? We looked at it and we had a very short study at NCM looking into the number of the operations. We took a year like a 2020, for example, and it was 390 operations done with around 1,000 hours. We look at the accumulated volume of the rainfall amount over the country at that year, it was 5.6 billion cubic meters. And when we looked at approaching only 50% of the suitable clouds, where it's not the case because we're always aiming to target 100%, but we just took the 50% as a minimum, and we took the 10% enhancement of rain enhancements. And of course, as I mentioned, we can reach also to 25%. So out of that, it was equivalent to 280 million cubic meters. Looking at the cost of the water, and within the study, it shows that it was a cost-effective approach. When we look at the ratio between the desalination costs and the rain enhancement or the cloud seeding, it shows 1 to 25. And this is as a minimum because we took a 10% enhancement only out of this cloud seeding operation. So with the total cost of cloud seeding operations in 1 year, which is $3.5 million, you can find the cost of the desalination in the other side is $86 million. And there is a very big difference here. When it comes to the when we say it's environmentally friendly technique, we do mean it because it doesn't have any negative impact on environment. And this is what we're really always making sure that even with the new methodologies, new materials, new techniques, or even with the methodology we use with our aircrafts and the flares that are used and manufactured here in the country, we do take this into very high consideration. We look into the environmental impact of that, and we have a yearly assessment in collaboration with the Environmental Agency in Abu Dhabi. And this is done in several parts here in the UAE. We always do that during the last quarter of the year. And so far, no detection of the materials shown, not in the surface water or the groundwater or the soil. And nowadays, we started also for this year. So we started one week ago for the assessment of this year. Nowadays, we're in the 6th cycle of the program. And as I mentioned, we look at it as a very long-term strategy. So we are always committed to support the scientists and researchers all over the world. And we're always committed also to connect them with the needed policymakers, government, private, all sectors to make sure they also support them in whatever they are progressing in their projects. So far, we are in the 6th cycle, and we will be announcing, we went through, of course, the submission phases, because this is the way how we collect the innovative ideas, through proposals and then 2 merit review process, stages, and then out of that we announce the awardees at the beginning of the year, and we start with them a 3-year research journey with an agreement with them. We look at, when we evaluate these innovative ideas, we make sure that those ideas proposes research excellence, impact, and quality. Do they have experience? We look at experience and how solid the team are. We look at the multidisciplinary collaboration and take it in a very high consideration, and the potential to enhance or transform the weather modification research community worldwide. When we talk about the support, we're not supporting only through the grant, but actually we're working with them in a joint team. So from a part of NCM R&D support, we do support them with continuous technical support and assistance. We provide them with the needed data, facilities. The infrastructure of the center is always open to these awardees and to these projects. And we do support their experiments and their campaigns as well, field campaigns. From the secretariat side of the program, we monitor the awardees' project deliverables. We make sure to be with them in every step to face any challenge we have and to be part of any solution, giving them the advice whenever needed. In this particular cycle, we do focus on the most important 5 thrust areas, I can say, in this field, which is the optimized seeding materials, rain enhancement systems, autonomous unmanned systems, limited area climate intervention, and the advanced model software and data. And we do make sure that, as I mentioned, we reach into a demonstration level where we don't stop only with publications. So it's all in a way where it's able to be demonstrated, it's able to be implemented, and transformed into the operations happening here in the country. And as an aim of connecting these scientists, researchers, and connecting them with the other sectors, and of course also pushing the youth to be part of what is happening in this field, we do also have as an initiative a global hub for rain enhancement, which is the forum, the International Rain Enhancement Forum. And this is very important for all of them to be connected. A lot of benefits came out of this forum within the 7 editions, and the most important benefit is building the partnerships between each other, between different sectors, and between the scientists themselves. And of course, we do have also a webinar series that also supports in this one. Finally, I'll talk about how we're looking forward to that and in the future. We are looking ahead with the 2030 strategic goals. We do have a roadmap with a short-term, mid-term, and long-term roadmap for this field. Where do we want to reach in the future? So we aim to accelerate innovation by deploying AI-based cloud forecasting, advanced seeding materials, and autonomous aerial systems. We'd like to support the high-risk, high-reward research to make rainfall enhancement more scalable and sustainable in the future. We also look into this strengthening the UAREP's global leadership through deeper collaboration, as I mentioned, multidisciplinary collaboration. And we do promote highly and strongly the knowledge and technology transfer in the field. We also look into integrating the rainfall enhancement technologies into water resource management to support vulnerable communities in arid regions. Thank you very much. I think I'll be available here the whole day in case there's no any time for questions.
Anyone who would like to ask any question? We have time for 1 or 2 questions.
Thank you, Ms. Alia, for a wonderful presentation. It was very, very helpful here. I'm particularly interested in how technology has evolved in this particular initiative. So can you tell more about the nanotechnology, or are the nano substances being created, the agents are already being deployed, or at what level the nanotechnology is being implemented, as well as the UAV, the drones, how they are being implemented?
Sure. Let's start with the nanotechnology. So one of the, it was the first, actually the first cycle project we had. It's using the nanotechnology to develop a novel material. Now looking into this material and the difference using nanotechnology, what this added really actually to the materials we had. We usually use the hygroscopic materials, which are natural salts, more into the salts used for like the sodium chloride and potassium chloride. But with the nanotechnology, it's coated with titanium dioxide, with a 10% coat of titanium dioxide. Now again, looking into the how environmentally safe is this, a lot of assessments has been done to ensure the safety from the environmental side. And within the effectiveness of that, it has shown that it is 3 times better and more effective than the hygroscopic materials that are used in a lot of other countries. Of course, other countries also used silver iodide, I can say, other than hygroscopic material, but with the type, it depends on the type of the clouds we approach. So here in the country and a lot of other countries as well, they use hygroscopic material. And for them, this novel material out of using the nanotechnology added a lot of value actually on that.
Thank you.
Sorry?
UAV as well.
UAV.
Yeah.
So we are looking into using the UAVs and autonomous. So so far the concept of using UAVs in our operations right now, nowadays, we're not using it in our regular operations or others using it in regular operations, but it's used only for research purpose, proving the concept of that. So we've been using it in seeding operations and in the measurements done before and after. And right now we are putting it in one of the most important areas for for more
irrigation,
for further
irrigation. Yeah. Thank you so much. That's so nice of you. It's a very wonderful presentation. Thank you.
Thank you, Ms. Ahmed. Thank you. This concludes our first session. We'll take a quick break and we'll be back at 10:35. Thank you for all our speakers and our attendees.
Okay, so welcome back. My name is Armin. I'm with the University of Hertfordshire in the UK, and I'm privileged to chair this very interesting session on heat waves. So we've got a list of exciting presentations from some of the most distinguished scholars and researchers and colleagues in the field. And the session is titled Data-Driven Insights into Heat Wave, Mortality and Climate Impacts. Each presentation is 20 minutes. After the presentations, I will invite all the presenters to join me on this panel, and we'll take questions at that point, if that's okay. And the presenters, please do stick to the time. So if you see me flying with 5, it means 5 minutes left. So we're sitting in that corner, and I'll try to give you a nudge to say that your time is, right, so the first presentation is titled Project Heatwave, Advancing Climate Health Resilience Through Science, Policy and Innovation. Presenters Dr. Anna Berstein and Dr. Alex Azan. Who is presenting? Yeah.
Thank you so much. And I just want to start by sharing my gratitude with the organizers of this conference, who are also really the conveners for Project Heatwave. It is an international collaboration titled Heat Emergency Avoidance Techniques Working to Adapt to Vulnerabilities Equitably. And so although it is winter, it's fitting that we are sitting today in one of the hottest inhabited places on Earth, discussing the health implications of extreme heat and what can be done. And so for those less acquainted with the health aspect of extreme heat, let me just start by defining what is heat stress. And we know what heat stress is through 2 scientific techniques. One of them, we have one of the most acclaimed scientists, Rob Mead, who will come after me, who essentially studies what happens to people when they're put in very scientific saunas, at what level of heat, humidity, wind speed, exertion does core temperature start to rise above healthy levels, the heart starts to show stress, other forms of stress. And we can also see this in the day-to-day lives of people who work outside in extreme heat, from construction workers in this region, potato farmers in Australia and Spain. And when those people's core temperatures and body functions are monitored, they also start to show forms of heat stress. And by looking at what environmental conditions correlate with signs of stress in their body, we learn that there are different measurements we can make of the environment that are predictive of that stress. And it turns out the temperature you see on your weather app, that's the air temperature, is only a very weak correlate of signs of heat stress in the body. Here we have one particular index of stress called wet bulb globe temperature, and that finds that only 10% of that stress can be explained by just the air temperature outside, just the temperature of a thermometer put outside in the shade. 70% of that stress can actually be attributed to a different measurement, which is called the wet bulb temperature. And wet bulb temperature is that same thermometer, but if it's kept wet at all times and the wind blows on it, and so of course that thermometer will be cooler, except when humidity is very high. So at 100% relative humidity, the wet bulb and the dry bulb temperatures are the same. And then about 20% is the black globe temperature, which is the temperature of a thermometer painted black, put in the full sun, so it takes into account the radiation of the sun beating down on a person. So why am I telling you about all these different kinds of thermometers? Why does that matter? Well, because we've just learned that wet bulb temperature is the biggest predictor of signs of heat stress on the body, and at some point that stress becomes fatal. And so we know that one absolute threshold for survival is a wet bulb temperature above 35 Celsius. That's the gray line that you see here. And what that means is if the relative humidity were 100%, it would only take 35 Celsius for everyone to die. So it's not such a high temperature. Of course, as you bring down humidity, you can bring up temperature to make these conditions survivable. And Rob will tell us more about how in very humid heat, the sticky heat that we have here in the UAE, the wet bulb temperature is a pretty good marker for that survival limit. In very hot, dry places, so if you go out for a hike way into the desert regions where it's more arid, actually your skin is no longer wet. Your sweat is not pooling and falling on the floor anymore. Your skin is dry because your sweat is evaporating and cooling the body. And so it's actually how quickly you can sweat that determines how quickly you can cool your body. And so it's actually limited by the sweating rate and doesn't go all the way to that wet bulb temperature because at some point you just can't sweat any faster. And unfortunately, as many of us know, children and the elderly cannot sweat as quickly as healthy young adults. The major problem that we as a project are facing is that there are 1 billion people with a B who live in places where climate will exceed those survivability thresholds. Now, of course, that doesn't mean every one of those people has to die. In this region, or along the coast of the Arabian Gulf, there have already been weather station readings exceeding that threshold, and thankfully, people can take shelter with infrastructure, with air conditioning. But that will not be 100% of people and 100% of the planet. And we know already that wet bulb exceedances of that temperature have doubled since the beginning of the 1980s. So it's a problem that is on a global scale, and this region of the world knows better than anywhere how to cope with this problem. How can we expand the lessons learned and keep the globe safe from these life-threatening exceedances? And when I say the globe, this is just some maps of where temperatures will reach or exceed these thermal compensation limits. So as you can see across the top, the coast of the Gulf is particularly prone to this because you have very hot water in the Gulf, you have a very hot desert, and then it's very humid at the coast where people love to spend time. It's beautiful, but you have that combination of heat and humidity that's quite problematic. But it's also a huge problem. Probably the next in line to experience these exceedances will be South Asia, the band shown there, Eastern Asia, North Africa. The United States depends on the warming trajectory. We're not quite, where I'm from, headed quite as soon for that kind of a scenario, but it's a problem that's going to spread throughout the world as we reach different warming thresholds. So I'm just going to go back to say, I forgot to mention this book, The Ministry for the Future. I wonder if anyone in the audience has read this book. It's a book that it's a science fiction piece that opens with a chapter describing what would happen if there were an excursion, a thermal excursion, a heat wave, that exceeds survival thresholds in a theoretical village in India. And it's told from the perspective of people there on the ground, and it's very gripping. So I wouldn't read it as bedtime reading, it will keep you up at night. And then the rest of the book talks about how the world reacts to that and kind of how we as a species adapt to extreme heat and how we take measures to deal with this. And so we don't want that mass casualty event that's described in the book to be the catalyst, because we have all of the scientific knowledge in this room to tell us that we can forecast in advance. We can use models to tell us that we're heading toward this calamity. We don't actually need the calamity to be the catalyst for a response. So I do recommend reading this book, at least chapter 1, if you haven't read it already. And the question is really, can we prevent this science fiction from becoming science fact? And I believe that through innovation we can. And that innovation really boils down to 3 pillars. The first is, can we forecast heat stress? Can we provide early warnings? Can we look over the long term at what geographies are at greatest risk of heat stress? And that includes really understanding the climate system and then also really understanding the human body and how different segments of the population can endure heat in different ways. Secondly, can we innovate new response tools? We, for instance, know that it takes the body about 6 weeks to adapt to heat. And that's why in the springtime, we tend to see more heat-related illness than in the summertime, because you're coming out of a cool season. Is there some way to accelerate that adaptation? What about medically? We know there are medications that make people more prone to heat stroke, but we don't know yet if there are any medications that are protective against heat stroke. Can we start that innovation process now for this tool that we know we'll need in the future? And we'll hear today about climate engineering innovations, about reinventing air conditioning and other members of the team that are looking for tools that need to be developed. The discovery has to start now so that the tools are available when we will need them most. And then can we put all of that together to evaluate different policy options in a digital laboratory that decision makers can use, where AI, I think, will be a giant accelerant of being able to simulate our climate, simulate our population, and optimize our response to extreme heat to keep populations safe. So really the magic of Project Heatwave is that we have this incredible spectrum of expertise that's been brought together, and we've been brought together here today across these different institutions with expertise ranging from the physiology and the medicine of extreme heat to real depth on the climatology, forecasting, downscaling, understanding what is the risk of a sudden excursion way above where we thought the climate would be, to the engineering, actually making new solutions to keep our populations safe. And this will really be showcased on the panel today, so I'm about to hand the microphone over to my colleague Alex Azan, who's a doctor who treats patients who are exposed to extreme heat, and it's a real-time threat to their health. We'll hear about forecasting heat and the risk of thermal excursions in the UAE, about intervening on the climate system, and then we'll learn about the body's heat resilience and talk about how we can combine that with AI-based climate forecasting to try to make population health predictions. And then we'll end with actually how do you reinvent air conditioning, which was, a 100-year-old technology never designed for today's climate in order to help keep our population safe. So let me hand it over to Alex to tell you a little bit about the medicine of extreme heat. And Alex, I'll pop your slides up here if I can find them. There we are. All right. Oops. Over to you.
Okay. Thank you, Anna. Good morning, everyone. As mentioned before, I'm Alex Azan. I'm an assistant professor at the New York University Grossman School of Medicine in medicine and population health, and I also, in that role, work as a clinician caring for patients in New York City. And so, as a clinical member of Project Heatwave, I'm hoping to convey to you all today, briefly, from a clinical perspective, why an initiative like Project Heatwave is so important and urgently needed. To start to understand what it's like being a healthcare provider, caring for patients during periods of extreme heat in our clinics and in our hospitals, I think it's first important to start by understanding what happens to our body when it's exposed to high heat. This is an illustrative diagram from Dr. Chris Ebi at the University of Washington that describes the main physiological pathways that occur when humans experience heat stress. And so when our bodies are exposed to high temperature, our brain initiates two main mechanisms of thermoregulation to cool us down. The first is on the bottom right side, in that circle, where a process called peripheral vasodilatation occurs that shunts our blood to our periphery, allowing heat from our muscles to move to the skin surface and back out into the environment. If this process continues and blood continues to be shunted towards our periphery, that can result in our blood pressure becoming lower, requiring our heart to beat faster and harder to keep up with thermoregulation, and if that continues, eventually that can lead to strain on our heart muscle. The other way our body initiates cooling is through sweat production. And so when sweat is on our skin and it's evaporated into the environment, it's one of the most effective ways our body cools in arid climates like here in Dubai. It's a little bit less effective in high humid heat regions where sweat isn't able to evaporate as well. Now, if the amount of fluid that we lose from sweat is greater than the amount of fluid we're able to intake to replace the fluid we lose from sweat, that can result in dehydration, which can further lower our blood pressure and that can even further strain our heart and start to damage organs that are uniquely vulnerable to changes in our volume status, like our kidneys. If a human isn't able to find cooling refuge and our core body temperature continues to rise, that can result in more blood being pushed to our periphery, a lowering of our blood pressure even further, and that starts to starve vital organs of oxygen that they need to function, in particular our brain and especially our colon. That can result in tissue death, systemic inflammation, multi-organ failure, and eventually is lethal. So as physicians, we see a wide array of presentations of heat illness that represent different points in time when a body is experiencing thermal stress. One main category of heat illness that we see in healthcare is it's categorized as heat-related illnesses. These are illnesses that are a direct result of the heat exposure. In high humid heat conditions, we often see heat rash because sweat isn't able to be evaporated as easily and it can irritate the skin. When people are starting to experience dehydration and their blood pressure starts to lower, we often see patients present with heat exhaustion, where they may have muscle cramps, fatigue, lightheadedness. And then in the most extreme and dire cases, patients can present with heat stroke, which is when tissue death is occurring, multi-organ failure is imminent, if not occurring, the death process is starting. And these patients need ICU level care. The other category of heat illnesses that we see in healthcare are called heat-associated illnesses. These are illnesses that occur when we have an underlying chronic condition and that condition is exacerbated from the strain that heat exposure puts on the body. So for patients with pre-existing cardiovascular disease, for example, they can experience heart attacks during high heat. People with chronic kidney disease can experience acute kidney injury and even renal failure. And people with pre-existing risk factors for cerebrovascular disease can experience strokes during periods of high heat. It's estimated globally that the number of heat-associated illnesses that we observe is much higher than the amount of heat-related illnesses. In the United States, where I work, the Centers for Disease Control and Prevention estimates that deaths from heat-associated illnesses occur at almost a 10-fold higher amount than deaths that occur from heat-related illnesses. And this doesn't even take into account the burden that the healthcare system experiences for non-fatal presentations for both heat-related and heat-associated illness. As Anna mentioned earlier, vulnerability to the health impacts from heat varies across different segments of the population. During periods of high heat, in clinics where I work or in the hospital, we tend to see the populations listed here on this slide present to us more frequently and in higher numbers. People experience vulnerability to heat for various different reasons. Some people have issues with thermoregulating optimally due to physiological constraints that they have. We see this in older adults, in adults with multiple chronic conditions, in pregnant women, and in infants. Other segments of the population are vulnerable because they are entirely dependent on another person to remove them from being exposed to high temperature. So we see that in young children and in older adults, again, who are dependent on their care. And then there are segments of the population who are considered vulnerable purely because of the exposure that they have to high heat because of their jobs, such as outdoor workers, and difficult social circumstances like people who are experiencing homelessness. And so to drive this point of heat vulnerability further, to make it clearer, I wanted to share this example that demonstrates how uniquely vulnerable older adults are to experiencing illness and death from heat-associated illnesses from cardiovascular disease. This is a global meta-analysis that was done a few years ago that synthesized evidence from North America, South America, Europe, and parts of Asia. Unfortunately, the UAE was not a part of this meta-analysis. And in this study, it was demonstrated that older adults experience a % change in risk of death from heat-associated illnesses from cardiovascular disease at a much higher rate than any other type of heat-associated illness, so looking at respiratory disease and cerebrovascular disease. And even though the % risk is higher for heat-related illness like heat stroke, the number of people who present to hospitals and healthcare systems for conditions like cardiovascular disease is much, much higher. And the reason why we think that this is the case is if you think back to that physiological diagram I showed before, when our heart muscle starts to be strained because we're shunting blood to our periphery, our blood pressure is lowering. If you have pre-existing cardiovascular disease, it creates a situation where you have a mismatch between the oxygen that the heart muscle needs to function, to keep up with thermoregulation, and the amount of oxygen it's receiving from a circulatory system that is in collapse. And that can lead to ischemia and infarction of the heart muscle and eventually death. So that's why we think older adults are uniquely vulnerable here. Heatwave is particularly interested and invested in understanding heat vulnerability comprehensively across all segments of the population, because when you integrate this evidence into climate forecast models, you can get a much more comprehensive understanding of the health threats that are imminent for the health system under varying degrees of warming. This is a paper that was based in the United States that showed the change in excess cardiovascular deaths from heat now compared to mid-century under moderate warming scenarios on the right and under severe warming scenarios on the bottom, where you can see the threat of cardiovascular disease-associated deaths from extreme heat increasing and growing geographically across our country. And so on this slide, I have a figure from the IPCC that shows how the increasing hazards of extreme heat and the increased amount of exposure that we may have to extreme heat as climate change worsens, and how those threats are compounded by the vulnerability that different segments of our population have, is what results in the heat risk that we see in our patients from the healthcare system. And so there are different ways that we as doctors and healthcare systems are trying to rise to this challenge of helping people manage heat risk in a warming world. And the first way that we do that is trying to optimize the way that we manage heat risks after they've already occurred. So one example I have on this slide it demonstrates how we manage heat stroke. On the right is a treatment algorithm from the New England Journal of Medicine. Briefly, I'll just share that this is an active area of research to try to optimize in hospitals and emergency rooms. When somebody presents with heat stroke, what we first want to make sure is that the physicians that are caring for a patient are able to recognize heat stroke really fast. So if I have an older adult coming to me in the emergency room during the summer and they have an altered mental status, I want to make sure that I can rule in or rule out heat stroke as quickly as possible. And that's because the way that we save people and save lives during heat stroke is initiating rapid cooling as fast as we can. The most effective way is through ice water immersion. There are different logistical constraints that health systems have to try and initiate this type of treatment, and so trying to understand ways that we can help healthcare systems better prepare for large amounts of people who may be coming in with heat stroke is one way that health systems are trying to invest in managing risk. For the sake of time, I'll be a little fast here. So the other way that health systems are trying to rise to the challenge of caring for people with heat risks is by understanding what our role is in responding to preventing vulnerabilities from these different sources of heat risk. And so how is the health system doing that? We're trying to reduce our contribution to the hazards of extreme heat by transitioning to renewables. We're trying to think of ways to prevent patient encounters with dangerous heat by making sure they know how to use their air conditioning unit, if they have one and can afford one, what they can do if there's a blackout or a brownout, how to access their nearest cooling center, and how to access emergency management services so that they know they're receiving messages to know when it's too dangerous to be outside. And then healthcare systems can also enhance the heat resiliency in vulnerable patients as well. And so a few different frontiers of research I wanted to briefly highlight that Heatwave is interested in exploring is that there is a growing frontier of research trying to determine optimal and feasible acclimation protocols for outdoor workers who may not be acclimatized to certain regions of the world. On the top is a table from OSHA in the United States that details how employers need to think about acclimatization in their health workers. They know, in their workers, they know how much time they should be able to work outside and for that to be safe. But there's also growing research trying to expand that science to other vulnerable populations. So this is a paper on the bottom that synthesized evidence looking at short-term heat acclimation protocols for older adults to try and enhance their heat resiliency as well. Another frontier of research in trying to enhance the heat resiliency of our patients is by using AI and other data science methods to determine precision heat risk prevention interventions. So what people like to call what's the CHAD2VASC for heat illness. CHAD2VASC is a precision algorithm that we use to understand with people with heart arrhythmias which patients would benefit best from being put on anticoagulant medication. And so if you apply that train of thought to medication for heat illness, one way of thinking about it, like Dr. Burstein mentioned, is there a combination of individual features that would make one considered to be of highest benefit for receiving a medication to prevent heat illness, to optimize their thermoregulation. So thinking of medications that can be used as prophylaxis in people who aren't able to optimally thermoregulate. And then the other way of thinking about this that I'm particularly interested in is in guideline-recommended medical therapy for certain segments of the population. Are there seasonal considerations we need to take into account to make sure that those medications are safe? So on the bottom of the slide is a figure from a German study a few years ago that demonstrated that older adults who were prescribed beta blockers and antiplatelet medications had a higher risk of presenting to hospitals for non-fatal myocardial infarction as a function of heat. And so if you apply that to patients with heart failure, for example, where beta blockers are a guideline-directed medical therapy that we give, are there certain patients that actually beta blockers, that we should adjust their dose so that their benefits continue to outweigh their risks even in hot weather? And then finally, I'll end by saying that a final frontier of research in healthcare is trying to tailor emergency management operations to individual level vulnerabilities. So currently in various cities across the world, this is an example from New York, epidemiological work has demonstrated that people present to the hospital for heat illness at lower temperatures than what trigger heat advisories, warnings from national systems. And so in New York, we reduced the heat advisory threshold to meet the science. And this is a natural experimental study that demonstrated that in doing so, we were able to reduce the amount of heat illness that presented to our hospitals in New York. Where healthcare systems fit into this is that we have electronic health records. We have very detailed information at the patient level. And so if you expand that line of research to electronic health records, there's a field of research thinking about how we can leverage machine learning and deep learning models to understand what particular sets of vulnerabilities a patient has that can be used to develop tailored heat safety messages through a patient portal, for example. And so on the right, I have an example from a climate and health hackathon that I helped moderate during Climate Week in New York City earlier this year, where the winning project proposal was just that. They had developed a proposal to create an AI-powered health and climate companion in your phone that takes electronic health record data and weather data and provides personalized heat safety messaging for at-risk vulnerable patients and their communities. And so with that, I'll end and move it to the next speaker. Thank you.
Thank you very much, Anna and Alex. Our next presentation is Modeling Climate Risk in Human Health, Science and Innovation Pathways for Cooling Interventions in the UAE by Corinne Hartin and Kelly Wanza from Silver Lining, USA. We'll take questions as part of the panel at the end of this session, so please do keep your questions, and of course we'll have that at the end.
Hey, thank you. I'm Corinne Hartin. Thank you so much for the invitation to speak today. And today I'm going to be talking about how do we go ahead and project the impacts of heat and through modeling. Nope, didn't change on the. Yeah, that one. Okay, good, thanks. Yes. Okay. Thank you. Okay, so with every increment of warming, regional changes become more extreme. And so what we've plotted here is temperature change on the top and percent change in precipitation on the bottom. And these are figures from the IPCC. So we have simulated change at 1.5 degrees, 2 degrees, and 4 degrees of global heat. And as I mentioned, you can see here that the regional impact or the regional changes are a lot more extreme than the global means. And so the arrow is pointing out kind of the Arabian Peninsula here, and we see that as global mean temperature increases, a significant change to the regional temperature here. And then we also see here in precipitation a lot of regional variability between whether places are going to get drier or places are going to get wetter. In this particular region, it looks as though it's projected to get wetter, however, not through just an average yearly mean, but through extremes in precipitation. So if we zoom in a bit more into the UAE here that I've plotted, that I'm showing in the red circle, this is some initial results looking at maximum wet bulb temperature along different global warming levels. We see, as we heard earlier, that this wet bulb temperature is a factor of ambient air temperature and humidity. And so we're reaching, as global mean temperature increases, we're reaching a significant threshold of that 35 degrees Celsius range. The UAE also faces significant vulnerabilities other than just extreme heat, things from sea level rise, storm surge, water stress, dust, sandstorms, etc. And so this has profound implications for the country's economic, environmental, and social well-being. And society faces a huge array of both physical and economic impacts. And we've heard a lot about morbidity and mortality from extreme heat. But there's also a lot of other human health impacts, such as changes in air quality from wildfire, from heat. There's changes in labor and supply productivity that we also heard a little bit about. Heat and learning, if children are exposed to hot conditions, whether in school or at home, they may learn less efficiently, and then therefore that translates into lower earnings in the future. Crime has also been shown to increase as temperatures increase. The energy system is also taxed under extreme temperatures, such as energy transmission and distribution, electricity demand and supply. Things like thermal cooling capacity also is really stressed. And then there's things like infrastructure, roads, rails, bridges, a whole host of impacts from sea level rise, impacts to agriculture, as we heard a little bit about, changes in forest. This comes particularly important when you're interested in carbon storage, freshwater resources, ecosystem, a lot of tourism, it will also be impacted. So how do we go about modeling all of this complicated integrated system? And the evidence for these economic and physical impacts is critical to policy development and decision making. And so we first start with scenarios, so big, large-scale global scenarios such as the RCPs or the SSPs. Those scenarios are then brought into an Earth system model, and the Earth system model is what gives you back these global fields. The information from the Earth system model is then passed into regional climate models because impacts happen at the local scale. And so Dr. Lamarck will talk about using some AI methods here in kind of this step 3. Then that information gets passed into sectoral models, so your energy systems, coastal properties, et cetera. And then finally, we can monetize and look at the impacts to those sectors. We're really interested in trying to understand where these impacts happen, when, and to whom these impacts are happening to. Just bringing up 2 examples of work done in the US. On the left-hand side, we have changes in air quality. This is looking at changes in ozone due to changes in temperature. And so in order to model that, we have to go through that whole series of steps. And it takes anywhere between a year and 18 months to get a study like this off the ground. So it's a lot of researchers and a lot of technical capability that is involved in estimating these impacts. And then over here on the right, we have projected change in future labor hours worked. And so if you are an outdoor worker, or if you're working in a unair conditioned like warehouse, which the US has a lot of, you'll be less productive, and you also might not be able to show up to work during certain hours. So things like that really start to impact the local communities. And I mentioned who is impacted is really important. So we've done a bunch of work where we're looking into vulnerable populations. And they happen to face higher risks from the impacts of climate change because they have less capacity to prepare for, respond, and recover from climate-related impacts. So with the same theme, we have air quality on the right-hand side under 2 different levels of warming. And we've looked at, this is children's health here in the table, and we've looked at the incidence of new asthma cases, emergency room visits, school days lost, infant deaths, and then hospitalizations. And we're trying to really get an understanding of who's being impacted. And if we look on the right-hand side, this is again, with projected labor loss hours. And we've looked at vulnerable populations such as low-income minority populations, no high school diploma, and older adults. And we can further break out the minority population into different groups that were found in the US. And we can begin to understand what groups are really being impacted. So our plan is to work with partners to apply these types of methods to this Arabian Peninsula and in other areas to quantify future extremes and the impacts. And then Kelly is going to talk about potential ways that we can reduce them through intervention techniques. Thanks.
Good afternoon. I'm Kelly Wanzer. I'm the executive director of Silver Lining. We are a nonprofit organization that's partnered with NYU Langone School, with Aviation University, and others on Project Heatwave. My organization focuses on the safety and security of the atmosphere and climate. And I'm really pleased to be here with you today and to see the evolution of Aviation University and AI and looking at problems in sustainability and climate. It's a real pleasure to hear all of the presentations here. And with regard to the evolution of heat in the climate system and the impacts on the region and the things that we're talking about in Project Heatwave, unabated, what we know is that heat will continue to rise. And so as we apply AI and other intelligence tools to the problem of different interventions at the patient level, the population level, and the infrastructure level, at some point, if heat continues to rise, it will overwhelm various interventions. And to that end, scientists and others have started to look at interventions at the environmental scale, meaning the regional and global climate system. So I'm going to talk to you a little bit about those things and how they intersect with the analysis problems that you're looking at. But in particular, the techniques that scientists and others are looking at are techniques for increasing the reflection of sunlight from the atmosphere. And the most prominent forms of those involve releasing particles into the atmosphere, different altitudes, to slightly increase the reflection of sunlight. And one of the reasons that scientists are looking at that is because it's a phenomenon that keeps Earth in the Goldilocks zone. It's one of the ways that the planet regulates itself. And also because it's been observed in certain events and natural phenomenon, like when very large volcanoes erupt.
And so I'm going to see if this animation works here. When Mount Pinatubo erupted in 1991, which for you students, you won't have been alive, but for some of us older folks, we've lived through this. Particles were released forcefully all the way up into the stratosphere, and that resulted in a cooling of the planet of about 0.5 degrees C for between a year and 2 years. So we've all lived through this sort of cooling event of particles being placed into the upper atmosphere. Scientists observed that. It led to a recovery of Arctic ice. And so it's based on this type of phenomenon that some have suggested dispersing particles into the stratosphere. And in fact, there's been an escalation in research activity in the past couple of years, and even investment in private startup companies that would put particles in the stratosphere to cool the climate. And so in Anna's book, Ministry of the Future, that was the response to the extreme heat event. And so one of the things we have to think about is analysis of things like this. But I'll talk to you about the other method that folks are talking about, which sort of lifts off of the cloud seeding point, which has to do with something that's been observed when particles from ships enter into clouds and create streaks. So what you're seeing there is a bank of clouds off the Pacific West Coast, and those bright streaks in the clouds are created by the emission from ships. And globally, the particulate emissions and pollution are actually slightly brightening clouds, as well as sometimes creating haze that reflects sunlight. And together, those things are actually creating, I think I've got a little bit of messiness in my slide here, but are creating a global cooling effect. So globally, greenhouse gases from pollution are warming over the long term, but in the short term, the particulates and pollution are causing a slight brightening effect that's cooling the climate. And in the past year or two, as shipping emissions were brought down with regulation, there's actually been an observed increase in warming. And so that phenomenon is something the scientists are thinking about in terms of potential active measures to produce the same kind of effect, or even replace the one that we're losing by reducing particulate emissions for other reasons. So these are the sort of large-scale intervention approaches, and the second approach in the low cloud has some potential applications that are regional or more localized in nature, at least in theory, right? So the science is very early, and these things are very uncertain and not without side effects in weather patterns and other things. But in terms of regions where heat is escalating and rainfall is diminishing, there may be potential ways to increase regional cooling or change regional precipitation patterns in a way that helps to mitigate impacts. And that involves quite a lot of improvement in our analysis capabilities for this type of problem. So going back to some of the earlier conversations in Corinne's talk, there are a combination of tools that are needed to really be able to improve and make more accurate forecasts of what the regional and global climate system will do in longer periods of time. And these involve a combination of improving our direct observations of the atmospheric system, improving the global and smaller scale models that use physics processes to project the future of the system, and bringing those together with other tools for analysis, and particularly AI. So AI can play a really strong role in directly and analyzing observational data, particularly if we have ways to get more of it. And of course, we can use the models that we have and use AI to make emulations at large scales that we can then analyze and simulate forward. And so all of that comes together where in a world where people are talking about making large-scale interventions in weather and climate, and here in the UAE, where you're pioneers in interventions in weather, this is a place where this type of analysis may be really important for kind of your role in the world as well as the prospects for the region. and whether these things are positive or negative for the impacts here. So one of the things that we do in Silver Lining is we've worked with scientists, experts in the United States and other places to help identify what are the things you need to do if you wanted to accelerate improved understanding of what climate interventions would do, what a climate system would do. And so there are some certain ways where we need to improve climate model projections by improving our understanding of certain processes that are uncertain. And some of the biggest uncertainties are actually in the atmosphere that people are trying to intervene in, and particularly the way particles interact with clouds. And so there's some focus work to do to have better model representations of those processes. And one of the ways to get at that is to get more observations. And it turns out the same idea that people have of injecting particles into clouds, especially over the global ocean, which is where the pollution is more sparse and the real estate is big, is also one of the greatest areas of gaps in our observations. So we have some big observational gaps to fill pretty fast in the atmosphere if we want to do these problems better. And the good news is if we do that, there are a lot of aspects of these problems we can do better. And so what's exciting from our perspective is sometimes we haven't used everything we have. And some of what we have is we have transportation platforms, like we do here at Aviation University, that could carry advanced instruments for making atmospheric measurements beyond what they do today, which is mostly weather. And so we've done some pilots with agencies in the United States and other partners to put advanced instruments on commercial ships and planes. There's been one pilot on Alaska Airlines and one on United. And we've worked with Maersk shipping company where we have 6 different instruments operating on Maersk ships. Maersk recently offered all of their ships, which means that if we have pathways for resources, we could get a really good network built out of observations of the marine atmosphere. And if we did that, then we would need people applying AI tools to leverage that data, combine it with satellite data, integrate it with model data, and give us a better picture of what's going on. So we're pretty excited about this, and in the same way, aircraft can do something similar, but they reach up to high altitudes so they can get the whole column of the atmosphere going up and down. And for problems of greenhouse gases and aerosols, that's really exciting. So there's an opportunity to improve the global picture that's being partly driven by these questions of people making, the idea of pretty significant interventions in the atmosphere. And what we think is that if we're going to make any determinations about interventions like that, that data is crucial. Data analysis is crucial. And there's some work to do in terms of understanding the specific interventions. And it's really interesting in the context of Ali's presentation because some of the work here in the UAE at the NCM is globally leading in terms of these atmospheric processes as an applied activity. So it's pretty exciting to be here at this time and to think about the potential for improving analysis of these things in the context of what at stake, which in Project Heatwave is ultimately heat-driven mortality and outcomes for people. So in terms of a roadmap for research and outcomes for the region, we're hopeful that there's a lot of opportunity here for progress. Thank you.
Thank you, Corinne and Kelly. Without any further ado, let's move on to the next presentation. We're standing between you and your lunch, and I hate to overrun whenever I chair a session, and thank you in advance for sticking to the time. So the next presentation by Rob Mead from Harvard Chan School of Public Health. Rob, over to you. Should I get it?
Is the one there?
That's it.
Great, thank you. Good morning, everyone. First off, I just want to say thank you for having me, and thank you to the presentators from Project Heatwave who actually made my job really easy, giving the background on thermal physiology and health impacts. As Anna mentioned, I'm a thermal physiologist. I currently work out of the T.H. Chan School of Public Health at Harvard University and the Salata Institute for Climate and Sustainability. We've seen a lot of projects today already with big global views using satellites and, big data sets. But I work mostly on persons, how people respond to high temperatures, how our body maintains its internal temperature within the limits it needs to ensure normal physiological function, normal homeostasis. A lot of my work has been thousands of hours in laboratory environments, but more recently I work a lot in field environments, particularly in India. And Alex did a really good job of setting the basis for this, so I actually can maybe get some time back here. But basically, all of the cells and physiological processes that occur within our body have evolved to do so under a very narrow range of temperatures. They work best under very optimal conditions. And so our body has developed a very complex thermoregulatory system to ensure its temperature stays within relatively narrow bounds. Basically what happens is, let's say we increase the heat of this room, we would have all of a sudden a mismatch between how much heat we are gaining from the environment and we're losing to the environment. This will cause our body temperature to rise. This temperature increase is sensed by thermoreceptors in the central nervous system in the brain as well as the skin, and then transmitted to the brain, which then initiates sweating and skin blood flow, which Alex had mentioned. But the goal of this process is basically to ensure that how much heat we're gaining, whether from the environment or because we're physically active, is balanced to how much heat we're losing. And a really easy way to see it is in this very simplified but common diagram in thermal physiology. This kind of shows how body temperature regulation works. On the x-axis at the bottom, we have body temperature, so mean body temperature. And then on the y-axis, we have heat loss and heat gain. So let's take a look at this, the light pink line there, a heat wave at rest. So again, I mentioned if we're exposed to a heat wave, we have this mismatch between heat loss and heat gain. Our body temperature starts to rise, and at a certain body temperature, sweating and skin blood flow are initiated. This is called the onset threshold. After that point, body temperature and heat loss increase in concert until basically one of two things happens. Either conditions are what we would call compensable, and a new balance is reached between body temperature and heat gain, or our maximum heat loss, our maximum ability to sweat is surpassed, and we can't actually compensate for the heat stress placed upon us. These are called uncompensable conditions, and this is what we're worried about when we think about wet bulb temperatures so severe that they basically surpass our thermoregulatory limits, and you can see that on the top there. On this figure, you can also see something that basically Alex mentioned, where certain groups, because of alterations in their ability to thermoregulate, for example, an older adult here on the bottom, has a slightly different thermoregulatory function. They start to lose heat at higher body temperatures, and their maximum capacity isn't quite so high. So what might be compensable for a young adult, it may be uncompensable for an older adult, and this is part of the vulnerability with certain conditions, with aging, that sort of thing. And you may have seen, and we talked about it a little bit already, this idea of why we're so concerned with uncompensable heat stress is because of the potential for these Ministry for the Future-like events where we have a densely populated region, we're experiencing wet bulb temperatures that surpass our ability to maintain body temperature regulation, maintain body temperature within safe bounds. And you might have even seen recently, there's been a lot of articles in the news suggesting that what we thought was the upper limits is maybe actually an overestimate. So we talk about 35-degree wet bulb temperature, but most physiologists would actually tell you that the true upper limit for thermoregulation is likely in the range of around 31 to 33, even as low as 26 degrees wet bulb temperature in a dry environment. So whether this is true or this basically, this is concerning because it's suggesting that we might actually be coming up against these Ministry for the Future-like events quicker than we thought we would. But there's an important caveat that I'll get to. But just to give you a little bit more intuition on what an event like this might look like, this is the last study I ran before I left the University of Ottawa. And what we wanted to do was basically look at how different wet bulb temperatures, particularly above and below these limits for thermoregulation, actually affect the body. So we brought a group of 12 individuals into the laboratory. We determined their upper limits for compensability for thermoregulation with a very common technique. It's called a thermal step protocol or a ramp protocol. And then we brought them back in and exposed them for up to 9 hours to wet bulb temperatures just above or just below these limits. You can see on the left-hand side, this is the just above condition, wet bulb temperature at 33.7 degrees. To put this in, I think here, use the heat index or the discomfort index. This is 67 degrees Celsius discomfort index. So these are very extreme conditions. And that's kind of reflected in these core temperature responses. They just shoot up and up and up. And we projected that individuals exposed to these environments would reach core temperatures associated with heat stroke, so around 40 degrees Celsius within 10 hours of exposure. Also, if you look at the 6-hour point and trace directly up, that's me. All physiologists, you have to, if you're going to ask people to do these extreme experiments, you have to be exposed yourself. So I can tell you firsthand that this was an awful, awful experience. I do actually want to, I wasn't going to cover this originally, but I do want to point one other thing out, is Alex also talked about the stress that occurs on the body, like the cardiovascular system and the kidneys, for example. And if you look at even the below compensability condition, even though this is a situation where body temperature is working, or body temperature regulation is working as expected, most individuals were able to reach some sort of equilibrium. Because temperature regulation is negative feedback control, this has to occur at a higher body temperature. So it's this increase in body temperature, strain on the heart, et cetera, that may occur over multiple days, months, during a heat wave, why we think that we see a lot more deaths due to cardiovascular conditions or diseases than we do to heat stroke and heat waves. But back to these kind of idea of upper limits for thermoregulation, when we actually try to align these with the epidemiological data, we run into a little bit of a problem. So this is a very classic kind of curve in environmental epidemiology. What we've done here is we've set at the bottom here the mean daily wet bulb temperature, and then we've looked in Chicago at all-cause mortality rates. And so usually what you see is this sort of same pattern where as temperatures get warmer, we have this reduction in all-cause mortality as we come out of cold temperatures to kind of more moderate environments. Then we hit what's called the minimum mortality temperature. So this is the temperature at which risk is lowest, and it's indicated there by that red line. And then we see a very rapid increase as temperatures get hotter above that minimum mortality temperature. People start to die more frequently. This is all cause, so it includes things like cardiovascular disease, includes things like heat stroke. But if you look at the wet bulb temperatures here, and I put the little markers here on the x-axis, this minimum mortality temperature and this swing into heat-related mortality starts to occur at much lower wet bulb temperatures than our suspected limits for thermoregulation. So basically what we take from this is that these limits that we were discussing and are in the news a lot now, they basically tell us when, for lack of a better phrase, we're screwed, but we still have a lot of mortality, morbidity that occur below these limits. So it's not so easy as just modeling these limits, and one of the things we want to do in heat wave is think about not only the mortality due to heat stroke, though of course that's a big thing, but also mortality due to other conditions, as well as morbidity. And this is just highlighting something that Alex already mentioned, that if you actually look at how people die during heat waves, this is data from New York City in 2024. Only 7 heat-caused deaths, so 7 deaths directly due to heat stroke. The rest were heat-exacerbated, and most of these occurred in individuals on the right-hand side here with cardiovascular disease or more than one chronic health condition. So again, it's less that they're surpassing these limits, and more so that it's just this constant strain on the body from having to thermoregulate. So these individuals likely die because of thermoregulation, not because of a failure of it. But the big question, and this is something I'm becoming very interested in, is this idea of how much we can adapt to coming increases. Certainly, at least not right now, most of the mortality we see from the heat is not due to these exceedances of these upper limits for wet bulb temperatures, but if they're coming, and we can hit these kind of mass mortality events like detailed in the Ministry for the Future, this is something we really want to know, because not only is it coming a risk, but also it has implications for the habitability of very densely populated areas of the globe. But one thing you might not know is what data is being sourced to make these projections. So Anna presented this figure here on the right-hand side. Again, these are projected exceedances of these new upper limits for thermoregulation, so in the range of around 30-degree wet bulb temperature. They're actually here. This is data from Penn State University in northeastern United States. Basically what they did was they did the same technique that I had said, that thermal step protocol. They estimated the thermoregulatory capacity of a bunch of young adults, and then they looked at a climate model, counted the number of hours in which these thresholds were exceeded, and then projected it out to the globe. And again, what they found was that in certain areas that are already quite hot and humid, areas like northern India, Persian Gulf, northern Africa, with further warming, we're going to see exceedances. But the issue here, I think at least, is the big assumption that's being made is that the thermoregulatory capacity of a young adult in Penn State, where the climate is quite temperate, our study was done in Ottawa, Canada, reflects that of individuals who are living, for their entire life sometimes in these already hot regions. So that's what we have to be asking ourselves is, to know how soon these events are kind of coming, does this data here reflect what goes on in these areas? And there's suggestion in the epidemiological literature that this probably is not quite the case. So these are some more of those curves I showed, produced from that same data set. This is actually what's called the MCC, the Multi-City, Multi-Country Collaborative, and they basically have linked temperature mortality data for 650 cities across the globe. And again, you can look at them and they'll have kind of that same pattern, a slow reduction of cold-related mortality and then this rapid increase into heat-related mortality. But if you look at the minimum mortality temperature, which again is this threshold for when we start seeing heat-related mortality, it's quite variable. I'm Canadian, Toronto is especially low, and this makes sense. We have a very cold climate. But if you combine this data from across multiple different countries, again, this is about 550 countries worth of mortality estimates, you can see this kind of pattern. If we start at the cooler countries down here at the bottom, we see a very low minimum mortality temperature. And then as conditions, we move up into these hot countries of Philippines, Taiwan, Vietnam, we have this shift to the right. So basically, higher temperatures, the minimum mortality is occurring at these higher temperatures. And if we try to see what best explains this variation in minimum mortality temperature, what we find is that the summer mean wet bulb temperature almost one-to-one predicts the minimum mortality temperature. Said a different way, the minimum mortality temperature occurs basically at the summer mean wet bulb temperature. And what this suggests, to me at least, is that humans, we are, whether it's through our physiology or our societies, are very adaptable to heat. And so I think we need to ask ourselves, is there a way that we can start to use this information to maybe change how we're thinking about these upper limits? 35-degree wet bulb temperature is meant to be a physically bound upper limit. The physiology would suggest that maybe this is modifiable depending on how much you can sweat. Maybe the true answer for Dubai, for areas like India, actually lies somewhere in the middle, and this is something we don't yet know. And then this will come up, I think, in Shannon's presentation, but another thing that we need to factor in here as well is that I've been talking about physiological autonomic thermoregulation, but most of our ability to thermoregulate is through behavior and technology. So this is a really nice figure from 1971. Hardy basically shows a range of temperatures from absolute zero all the way up to the surface of Venus, and you can see there the very small physiological band is completely dwarfed by our ability to modify our behavior. So this could be through very simple strategies. We often seek shade when it's hot. We can use electric fans. To much more complex adaptations, you could call them, that have allowed us to survive and thrive in the Arctic tundra, as well as in the reentry in a space capsule returning from outer space. The temperatures around the capsule, the plasma can get up to 3,000 degrees Celsius, and we never hear about astronauts getting heat stroke coming back to Earth. So this is kind of the question I guess I'm leaving to everyone, is, can we use AI to help us think about these limits for adaptation, how quickly they're occurring, how quickly we're actually approaching them? But one final thing I want to note here, and maybe some people in the room have seen this already, is the areas that we're most concerned with are also the areas we don't have any data. So again, this is the biggest compendium of mortality temperature data that exists, and we have basically no data from Northern Africa, from India, and very little from around the Persian Gulf. So I think this is, the big use case for AI in this space is as we begin to collect this data and better understand how thermoregulation looks in these areas, can we, pull in the data we have from other locations so we can start answering this question quickly, because as we've seen in the other presentations, this is kind of this is a running clock. We need to very quickly figure out what the future looks like in relation to heat waves. But I'll leave it there.
Presentation. Our next presenter, Jean-François Lamarck, Head of Research at Trican's Group USA, and the title is AI in Support of Quantifying Impacts from Climate Extremes. JF, over to you.
Thank you, and thank you for having me here. So I will be taking a lot of what has been discussed so far and put it more in the context of physical conditions, how those are going to be evolving into the future in terms of what a heat wave represents, and how, in terms of climate modeling, which is where my experience is, but also much more at the scale where it matters. So, let me see here. Okay, so basically the main things that I'm trying to solve here is really to try to have a discussion of the likelihood of catastrophic heat wave. So heat waves happen all the time. Sometimes they end up being really, really consequential. And so going into the future, we've seen this over and over again over the last few slides, looking at a 2-degree world, a 3-degree world, a 4-degree world. But what is, in terms not just so much of an average set of conditions, but in terms of extreme conditions, which is when we start having, because of the very strong nonlinearities of the system, we start having very consequential aspects. And so in this case, I will really focus it on how strongly would people be affected and where, trying to use, and then the consequence would be, then has been discussed already, what could be adaptive and protective measures that we could build ahead of time if we know what is the likelihood that there is going to be something. A heat wave, so this is a picture of a heat wave, I believe in 2004 over India and Pakistan. But a heat wave is a lot of very high temperature. There are a lot of details and structures to all this. And so it's not like saying that it's going to be a heat wave, that it means that there's going to be a heat wave that will be consequential everywhere over a very large area. And one of the examples to me that's very telling is what happened during the 2024 Hajj pilgrimage, where well over 1,000 people died. And one could think that this was a consequence of the fact that it was very hot for an extended period of time, and yes. But the actual conditions during which those were becoming very dangerous and lethal for adults or even young people was very variable on a day-to-day basis. The number of hours for which this was happening was very limited. So we're talking here about variations in time and space that makes it really important to capture if we want to be able to capture what is happening and what is the likelihood of happening. So again, I'm going to take this from a climate and weather forecasting space. So a heat wave, like even what we're describing here during the Hajj, is still a very large-scale physical process. This is a picture of one that was happening last summer, 2024, over Europe and North Africa. This is very large. We're talking about thousands of kilometer scale. And the physics of it is fairly well understood at this point. It's the generation of basically a heat dome, something that gets very isolated and becomes so stable with high pressure system that basically things start cooking inside. But so the very large scale structure is pretty well understood. The aspect here with AI is that over the last few years, let's say 3 to maximum 5 years, there's been a huge development in AI being used for weather forecasting models. So all those models are based on the existing data sets that have been created over the last few decades based on observation, blending models for weather forecasts, whatever we call reanalysis. And I'm happy to spend the details afterwards. I don't think this is critical for this. This is just 2 examples of what is being done routinely now. This is beyond just the research space, but this is on what is being done routinely at the European Center for Medium Range Weather Forecast, ECMWF, and I'm just picking here 2 examples, Aurora, ForecastNet. Those are 2 models, AI models. The reason for this is just to show that those models can do forecast every day, and they can provide something of a structure that looks very real. There is a little, one thing is that each of those models is about 1,000 times cheaper than the full physics model. There's a little bit of an asterisk here. Currently, those models do not do everything that full physics models do, and they have only a limited number of variables, parameters that are being studied. They usually focus on temperature. Humidity is not done very well, although that's getting better. Precipitation is also problematic. But at least for temperature, we can go already a long way. And they're kind of stuck for most of them at 25 kilometers, just because of the way the training data sets have been at this point. The advantage, though, is that they're 1,000 times cheaper, meaning that you can actually start doing ensembles. So ensembles is the main technique for people can have to try to identify extremes, right? And represent them explicitly, not just in a statistical fashion, but have an understanding of what is the general structure of what those extremes are. And so this is a simulation of a heat wave in the US. This is a paper that was that is under review right now, just published, where they created an ensemble of over 7,000 members. Weather forecast right now, it's done with like maybe 30 ensemble members. So the idea of being able to capture an extreme is much, much, much less likely now than it is with those. And the advantage is that here, what I'm trying to show here is the confidence on what we know an extreme is going to look like. If you have a small ensemble member, say 50 ensemble member, then the ability to show what an extreme is exactly going to look like is going to be much less uncertain than with a lot more ensemble members. And this is the critical part that AI is actually enabling right now, is to be able to have those huge ensemble members. Now the problem is we're still at 25 kilometers. 25 kilometers, thinking of the Hajj again, is what would separate some of the major sites over in Mecca. So we need to go beyond that. Some of the presentations earlier, I'm thinking here of the MIT lab, was really showing what were the structures inside of city of where heat or temperature is going to be. So if we're going to try to do something that is going to be very relevant to where people are, we have to go beyond those 25 kilometers. And for this, what I will be discussing here are what I would call several approaches where AI will be very critical in helping this. The first one is the same way we have had a collection of models that have enabled the creation of AI tools to go to the global scale, meaning the reanalysis. It is like, how can you take that and then go to the next step? There are a variety of very high-resolution models that are being used. One in the US, which is what I'm most familiar with, it's called HER, is about 3 kilometers of horizontal resolution, which means that, and that has been running for 10, 15 years. So you have enough information that you can start blending the large-scale structure that you know is being done properly by the 25-kilometer simulation, and then start blending that using the information that a 3-kilometer can do. And this is something that is being tested. There is the NVIDIA CorDiff approach right now, and so you can see that you can go from what looks like a 25-kilometer, what is a 25-kilometer structure here, which has, this is Taiwan. And so kind of like very smooth representation of what the structure looked like, to something that would be very equivalent to what is a very high-resolution model, in this case, WRF, would provide, and this is what AI can do. And again, AI will be able to provide you here the refining details of what is going on. You keep the overall same structure, the large-scale structure is the same in all cases, but the AI is being able to capture the details the same way a high-resolution model does. 1 to 3 kilometers is, I would argue, not yet quite good enough to really try to understand how and where the population will be affected. So there is the well-known urban heat island aspect to it, right? And so, oops, I don't want to do that. So this is a reconstruction of the urban heat island based on satellite data. We had the very nice introduction on satellite data, how they can be used, and what are the different resolutions that can be used. And this is a way of using that information to get, basically, if you have a certain temperature over a region, this is going to be the footprint. This is going to be the small-scale structure that you have to take into account, not say, and this is going to be 25C. Well, 25C is going to be 25C in a very small portion of it. And then where it really is going to matter is going to be around those corridors. And so so you can do it, sorry, this is very touchy. You can do it from satellite observations. Now we have something that is tens of meters, so you can start looking at the structure of the cities and the canyon of the cities. If that is not sufficient, then we can also start looking at using just AI the same way we've done in creating a collection of AI approaches, trying to cut down the resolution, is to go from a large regional model to a very medium regional model to what we call large eddy simulations. Large eddy simulations are now being used and being able to run on GPUs such that they're very, very efficient. So we can again start creating large-scale ensembles from which we can train AI systems. And then we can do that now with resolution that would be about in the meters. So to me, this is going to be what is required to really go from the large scale, which is what climate models do, all the things that we've seen in the previous discussions on, in a world of 2 degrees, this is what it's going to look like. Well, if we really want to do that, and we have the information, and it's a really clear request here to make sure that there is the local information that can be used to provide the forecast and the projections at the scale where it matters, then we will have the ability of using AI across all those to not only identify the structure, but also identify the probability of high-scale, high-risk conditions for that. So, and my big pitch here would be, in the end, this will only be valuable if there are local observations. And so it was very, very encouraging to see everything that was being done here in Dubai in particular. So with this, I'll take questions. Thank you.
Thank you, Jeff. Right, our next presentation by Professor Shannon Yi, titled Advancing Sustainable Cooling Techniques for Extreme Heat Regions, and Shannon is from Georgia Institute of Technology. Shannon, over to you.
Thank you all for having me. I'll be talking, I guess to shorten my title, just really about reinventing refrigeration, right? So in the face of a heat wave, what will people likely do? They'll go indoors and turn on the air conditioning, assuming you're lucky enough to have air conditioning, right? I think it's a fantastic solution. It'll allow you to live in very hot environments. You can build big, beautiful buildings, and you can rely on the refrigeration technologies that we have. Unfortunately, I kind of worry that those refrigeration technologies may not be good enough. So, looking to the future with populations rising, urbanization happening, and growth of GDP, we're going to see an increase in the number of refrigeration and air conditioning units that are deployed. Right? By 2050, it's expected that we're going to grow from about 1.4 billion air conditioning units in operation to over 5 billion units. In that time frame, the next 25 years, this represents roughly a $4 trillion opportunity. So I'm pretty sure we're going to see that. And vapor compression is wonderful. It scales well. It's modular. You can place it different places. It's efficient. It's reliable. It's cheap. The downside is it only hits about 14% of its theoretical efficiency limit, and it has pretty appreciable global warming potentials with the refrigerants that we have, several thousand times worse than what we would have with CO2, right? So if we continue with this, business as usual, this will by itself end up representing global emissions between 7 and 19% of all CO2 equivalent emissions just from that one sector, right? So something we should definitely consider. There have been proposals for other types of refrigeration and cooling technologies, largely referred to as not-in-kind technologies that have zero global warming potential. The problem here with all of these different cycles is they're expensive, they're even less efficient, and they can only find their way into niche operations. So for me, from an engineering perspective, this is where I get excited because there's a real opportunity to come back and say, okay, what technology can we deploy that really poses the question, can we reinvent refrigeration, right? We need to come up with new technologies that are cheaper than the incumbent, really hard to do. Vapor compression is really cheap. And we have to make it much more efficient so it costs people even less to turn on the air conditioning. And I think there are pathways, given that we're only at about 14% of our limit. Air conditioning, refrigeration, have a very rich history, right? Some of it actually ties to this university. We've had artificial refrigeration for a long time, but it really is only within the last 100 years that we've seen it be commercially viable. So one of the first commercially viable system was a home compressor-based unit developed by Alfred Mellows. Fun fact, for the Emirates Aviation University, you're closely tied to the Wright brothers innovation. I grew up in the hometown where the Wright brothers invented that technology, and it turns out Alfred Mellows is also from that same location in Dayton, Ohio, where he invented this refrigeration technology, creating the Frigerator, which became Frigidaire. Right? So that's where refrigeration came from. And this is a really, really, really hard engineering and scientific problem. Albert Einstein, as many of you know, was a patent attorney, or he was in the patent office, an examiner, that's the term, patent examiner. And he had an idea for this Einstein refrigerator, but he could never get it working. So he ran into another patent examiner by the name of Leo Szilard, who actually got the engineering done that the physicist wanted. And they got this refrigerator working in the 1930s. And that was the first collaboration between Albert Einstein and Leo Szilard, who then, both of them went on in the Manhattan Project. And the amazing thing about that era, back in the early 1920s when air conditioning was coming, is we also had the internal combustion engine, right? The Model T was out by then. In 1927, you then had the Model A, but we're just in the Model T phase. And if you look at what's happened over the last 100 years, we've now moved from internal combustion engines to electric vehicles. So we've started to implement electrochemistry to replace a mainstay of mechanical engineering. If you look at refrigeration, however, there's Frigidaire's original refrigerator from the 1920s, and here's a home unit. There's not much change, and that is very true. A lot of this relies on thermodynamics. So I'm going to go into my professor mode and talk about thermodynamics. We rely on specific thermodynamic cycles to do most of this work, right? For power generation, we're heavily reliant on what is known as the Rankine cycle. We boil water, we turn a turbine, we generate power. So that's 70%, right? If we look at the Al Maktoum Solar Park, it has a large array of PV cells, photovoltaic cells, but it also has the world's largest concentrated solar power plant, which also runs on the Rankine cycle. To make up this other 30%, we have cycles like the Brayton cycle or the Stirling and Ericsson cycle for different CSP applications. There are other cycles that we can also turn to for vapor compression. So if I look at refrigeration, it's all about this vapor compression cycle. 95% of all air conditioners and refrigerators rely on this. It's basically running the Rankine cycle in reverse. So instead of boiling water to turn a turbine, we compress vapor and allow that to condense. Right? So we're just running that cycle in reverse, and that's in every car, every building, every refrigerator, every dehumidifier, every air conditioner. It's what we use, right? It works fantastically. It has two heat exchangers. It has a compressor and a simple expansion valve. We teach this to mechanical engineers all around the world, but we also teach them about another cycle. We teach them about the Brayton cycle. So I'm showing the Brayton cycle here as a refrigeration unit where you can drive a compressor, go through some heat exchangers. You can recover some of that work with a turbine. It has a downside. It has a very small temperature lift between hot and cold temperatures, but it's something we can do, and we actually use this pretty extensively. Right? This is the core cycle that makes up Emirates Aviation, right? The Brayton cycle is what powers jet aircraft engines, right? We take air, we compress it, we combust some fuel to heat it up, it goes through a turbine, and then our planes take off. So thermodynamics is very real. So when it comes to cooling, one concept we had several years ago was, okay, if we're going to be looking at thermodynamic cycles and we're going to be realizing the transition to electrochemical systems, could we create an electrochemical Brayton cycle? And in fact, we did. This was the first demonstration of continuous electrochemical refrigeration in the world, and we relied primarily on the Brayton cycle to do this. It has four major components, two heat exchangers, one where we absorb heat, another one where we reject it, and then it has two electrochemical cells, one where we put electrical work in, just like you would have with a compressor, and then one where we recover electrochemical work in the form of electricity as we discharge it, and we can connect those together and make it really efficient. You can work through all of the thermodynamics. You basically are having to do what is known as isentropic electrochemistry. It's difficult to do, but doable. And then you also have to look at all of the irreversibilities, those sources of entropy generation, and try to optimize all of this. So after doing that, we assembled the system, just consisting of a couple of pumps, some heat exchangers, and electrochemical cells, and we were able to demonstrate using a very classic couple, the iodide-triiodide couple with ferrous-ferrocyanide, that we indeed could witness electrochemical cooling. Right, so we repeated this several times, just kept running it, and then started characterizing it to see how well it performed. Most of the time, we're interested in the coefficient of performance. That's a measure of the efficiency and what the overall heating load was. So this was a small cell, about 8 centimeters by 8 centimeters, but the first time we ran this, we ended up with a coefficient of performance of 8. Right, and to put that in perspective, the coefficient of performance for vapor compression, which is cooling this room, is only about that of 4. So the first time we built this, we had an efficiency that was twice as good as the incumbent technology, pushing about 30% of that Carnot limit. So this gave me a lot of encouragement. It gave us a way to actually take this one step further. And a lot of that comes down to really understanding the entropic potential that's behind all of this. So I'm going to show you some interesting entropy diagrams. So on the left here is a measure of the entropy normalized by the specific gas constant. That gives me a dimensionless quantity that represents the amount of entropy change that would happen per carrier. And we're comparing it against other refrigeration technologies. Starting in the left, we have magnetocalorics, then we have thermoelectrics. The blue is vapor compression, yellow is metal hydrides, red's absorption refrigeration, and the green bar here is electrochemical refrigeration. And you can take that back to the fundamental processes. For vapor compression, we get that entropy change going from a liquid to a gas. In electrochemistry, we actually get a solute-to-solute entropy conversion that corresponds to the solvation entropy of molecules around an ion. And I get excited about this because I have a 6x potential in the amount of entropy compared to what I would get from a liquid vapor. So fundamentally, I have a 6-time greater likelihood to achieve that high efficiency. So that got me really excited. It also turned out to get other folks really excited. So since then, there have been a lot of people evaluating what they can do with electrochemistry and making other types of refrigeration. This is one known as an ionocaloric refrigerator, where you basically use electrochemistry to separate different materials, you crystallize it, and then use a melter in order to recover some of that entropy. So again, just melting things. And that has even expanded to look at what is referred to as dipolar caloric refrigeration, where you can actually separate two sets of ions and again still have a melter. Right? Both of these technologies have shown a slightly larger delta T, but their coefficient of performance is still very low. Right? And that comes down to, again, the source of entropy. For us, we want to do it directly. Other groups want to do it indirectly, just by melting things. But what I want to leave you with is how we can get this to be even better. Right? So, following the Brayton cycle, one thing you can do is multi-stage intercooling and multi-stage reheating of your turbine and compressors. Ultimately, what that gets you to is an isothermal process, right? That's always our goal in thermodynamics. And so there's another cycle out here known as the Ericsson cycle. Theoretically, it can achieve the maximum efficiency of a reversible heat engine, the Carnot limit. And we've been able to vision how this would actually work electrochemically. So we would simplify our system down to just having one heat exchanger, one regenerator, and then we have to balance what we do with electrochemistry and heat transfer. In doing so, the overall TS diagram, the entropy diagram, starts looking more and more like a rectangle. So with this, I should be able to be pushing closer to about 60% of the theoretical limit once I take account of all of the irreversibilities. So from my standpoint, when I look at addressing heat waves, I'm pretty sure we're going to go inside and turn on the air conditioner but we need to make a better air conditioner in order to get this out to the rest of the world. So that's where engineering comes in to come up with new ways of reinventing refrigeration. So thank you.
Thank you very much, Shannon. We have a short panel, so I would like to invite the speakers to join me on the stage, please. And we can take questions from the audience. We try to finish the panel discussion by 12:30, so bear with us. Right, so keep your questions coming. So do we have any questions from the audience, from any of the speakers? No question? Right, so is there not? Right. Okay, so thank you very much. Very interesting set of presentations, excellent research, very diverse as well. Engineering, the socio-economic side of things, AI. So how would you guys manage the diversity of disciplines that come into this Project Heatwave?
I think the diversity of expertise that you see on the stage is the point of Project Heatwave. These extreme heat events can't be solved by any one discipline alone, and it also probably can't be solved with the technology that we have today. It's going to require AI, it's going to require pushing the limits of climate science, of engineering, of medicine, because of just the sheer scale of the problem.
Right, thank you. What are, I think we will need to turn that off. Thank you, thanks very much. So what are the benefits of the project for the, how do you see the findings could be contextualized within the context of Emirates? Who would like to take that? Kelly?
Excuse me. So I think that what was pointed out in some of the presentations is there's a need to adapt the tools that look at regional and global climate for the region, and an opportunity for researchers here to help in that task. And at the intersection of what Jean-Francois and Corinne were talking about, which is kind of cutting edge tools, especially interfacing with AI, there's a real need to sort of map the future of the region that, partly is helping to advance the ability to map the future of any region. So I think that's exciting. It also sounds like the UAE has an opportunity to help accelerate the collection of data that applies to these problems, both at the patient and healthcare level and at the environmental level. So it's quite exciting overall. I think that the capabilities here can help accelerate knowledge for the region, but also the tools for the world too.
I think another aspect of this is looking at the technology that's deployed. So we all know when you're running your air conditioner, it costs quite a bit in electricity, right? So if we can develop technologies that are more efficient, it's going to save people money. If you can develop technologies that are modular, it enables new types of architecture. So I think from my standpoint, how it helps the UAE is it helps it flourish, right? Saving energy, being able to have environments that are habitable.
So one thing that was present in Corinne's presentation was that there is the projection that precipitation over this area is actually expected to increase by quite a lot. And so I think more generally, this area will be subject to very significant climate impact if we end up in very warm world. And so this will, the fact that there are programs like NCM that has been taking a lot of measurements over the last many years, you actually have good understanding of what is the basis, where are we now? Because if you don't understand where you are now, it's going to be really hard to understand how to adapt from here. And so I think there is a huge potential here to take advantage of all this maybe at this point disparate pieces of information that people have, but really to try to combine it together into a full understanding of what are the future conditions here.
Thanks for that. Yeah, of course, yes.
Hello, everyone. Thank you for your talks. A lot of the presentations have been about evaluating and predicting. Are you also looking at, once there is a technological or societal solution, how to implement that with society? Because, it's easy, from an engineering perspective, having, aircraft without pilots is probably safer, but I don't think I would ever want to get on an airplane without a pilot. And I think so preparing society is probably a really big part that we don't really think about. What are you doing to that end is my question. Thank you. I don't know who that question is directed to, but
I would say the roadmap for this project spans from the basic discovery, the basic epidemiology, through to the applications in society. And what that's going to require is really partnering with decision makers, leaders, and communities in these extreme heat geographies. And so where we've begun is to start establishing those partnerships here in this region and also in South Asia. I've just come back from a trip to Bangladesh, to Dhaka, sponsored by Project Heatwave. Flew on an Emirates flight and was able to speak to researchers there that are working in urban slum communities where heating, due to climate change, is accelerating even relative to Bangladesh as a whole due to the urban heat island effects and the fact that people are living under tin roofs. It's just sweltering hot in those homes. And really, I think this group of scientists that you hear from, we hope to be the innovation engine, but we hope that we have spokes out to people who work in those communities. A decision maker in the UAE should not have, a scientist in another country on speed dial. They have you all on speed dial. And that's exactly why we're here in the Emirates. We have to build those partnerships so that the people who are working in the ground, who are living in these communities, who the government knows to rely on because you're the partners, that are here for them day to day, can have you in order to move those innovations to reality.
So from the modeling standpoint of things, the first image that I showed of scenario development, and so a lot of kind of human system modeling goes into the scenario development. And so if you have, there'll be different technology uptake and different rates of technology uptake in different countries, right? And then that gets translated then into global emissions, which then filter through the chain of command into global climate modeling to regional modeling. So there's a lot being done under the hood in that scenario model development to try to get at those regional technological changes.
thank you again. I've seen a lot of projects like yours fail just because there's so much diversity, which was, I think, the first question that the host asked. because everyone pulls in the different directions, and it takes a lot of time for people involved to try and understand what everyone else is talking about, because they use different terminologies, different things, different priorities. How do you feel you differ and you're going to succeed?
Hello? Okay, great. I know it's a great question. I think what makes Project Heatwave unique and what Anna laid out so clearly in the first talk is I think we do have a really well thought out framework that brings each of the different components of Project Heatwave into one clear, cohesive plan to inform heat action plans to protect people in the here and now, with, trying to address the problem that how heat is impacting health today, but also plan for future extremes where we don't have the technology yet to save large parts of the population. So to me, I think why Project Heatwave works is that I think it's kind of the opposite, is that if you focus too much in one direction, you solve a problem in a very sort of narrow-minded way, but with all of the different components of Project Heatwave, we're able to plan for problems that are here now and problems that are coming in the future, which is, I think, what a lot of our stakeholders are asking for. So, yeah.
It was a nice presentation by all of the team members. I just wish to know the problem you are addressing based on the heat waves generated through natural process or human-induced heat waves. Like when you are working with a lot of industry, or like now data centers are coming that are generating a lot of heat generation. So like refrigerator you discussed, different area you are discussing, it's our human-made heat generation. The problem we are going to address is human-induced heat generation or a natural-based change in the climatic conditions. So, and how it can be addressed whole together. Like it's involve different factors, different data sets you require. So based on that, how it can be implemented in a real life.
Sure. I think what we're learning is that the heat wave problem is not an isolated natural phenomenon, because how we experience heat depends on the infrastructure that we have. And as you've alluded to, our infrastructure can create heat. For example, cities are warming at twice the global average because of the heat island effect. And we have some, technologies already for how to mitigate it. We can paint everything white to be reflective, but those technologies are inadequate for the climate that we're heading for. So we believe that it's necessary to innovate in order to, build cities that are resilient for the future natural environment and to keep our health safe.
Right. Thank you for the questions from the audience. And I've got a question for perhaps Rob or Alex. We talked about the health outcomes of heat waves, and I'm really curious, about this. What about mental health outcomes? Is there a sort of quasi experiment to model and see, how it would impact, anxiety, depression, PTSD, other forms of known mental health outcomes when it comes to heat waves? There's a lot around morbidities and what it does into, the physique of an individual. What about mental health? Thanks.
Yeah, that's a great question. There is growing recognition of these kind of cascading impacts, maybe more indirect impacts. We talked about cardiovascular events, and now, as conditions get hotter and we get more and more epidemiological data, we know that heat waves will increase hospitalizations due to mental health effects. I would say that the research community is well attuned to this. I actually just sat on a welcome committee that will fund, it should be announced soon, a whole host of grants looking at the kind of mechanistic relation between heat and health. So not just saying, when temperature goes up X, mental health hospitalizations go up Y. And because of the way the heat wave platform is kind of structured, this will be information that as it becomes available, we can start to incorporate either directly with the researchers or just, considering how we can think about it in terms of these like upper limit thermoregulatory models, epidemiological associations. So basically, the research is coming, and when it comes out, we'll incorporate it as best we can.
Well, yeah, Alex, good. Any contribution from you? Are you okay with what Rob added?
I think that was a really comprehensive response. I think the one thing I would add too is, beyond just the physiological impacts of heat, I think that the cascading health impacts of, the cascading impacts of extreme heat events are not just physical. There are things that it can do to our society, right? People read things online about heat waves that can impact their mental health. And so I think, as Rob said, the science is just beginning. And it's definitely something that I think, Corinne, you had mentioned, we need to be comprehensive in thinking about how we integrate that into our modeling. Yeah.
Excellent. I think we've got a few more minutes. I'm getting signs that we've got a few more minutes of freedom to talk about this exciting project, and there seems to be some questions in the audience as well, which is fantastic. So let's pass on the mic.
Okay, I have a question. As you discussed in previous presentation about the AI system that detects the heat waves or hazard, do you think it will improve over time or independently over time? Because as we know that climate change, it's like change over time. So what do you think if AI will like change also, it will improve over time?
Yeah, that's a great question, right? It's that AI requires data, right? You can only, with some confidence at least, use the existing data and then use AI to reproduce what is within that space. Anything that's outside risky at best. So I think the only way forward is actually what was described in one of the presentations, to have a continuous cycle of observations that would basically educate the system along the way. It's not. I think one of the dangers that AI is bringing is that the problem is solved. We have those very great AI now. They're cheap and they can do everything. Well, this is only going to be good as the data that you can put in there. So really integrate it and make sure that there is considerable evaluation along the way, and make sure that the system evolves. It is going to be the only way it's going to work. But the more we use the system, we can start building a system and start using it and testing it along the way, is the best way to improve it.
And I think we also need to couple that with physical-based modeling as well in order to do the projections and then ground truth the AI. If the AI is using current observations or historical observations, then we can use the physics-based modeling to then project those changes in the future, and then AI can help us with that as well.
I'm just thinking about, I don't know if you're familiar with the Cynefin framework that we sit with. Climate change for us is actually chaos. We're actually not sure what's going on. But how do we use AI to bring it back from that chaotic disorder state to being a complex or a complicated state that we can manage? So that's what I'm alluding to, that, and your team is actually doing exactly what we need to do much more of. This multi-interdisciplinary, not each working on your own thing, but learning from each other, and that's how we're actually going to solve this issue, is by bringing this diverse people. Engineers should not be talking to doctors. It's crazy, but that's exactly how we're going to solve this, is by bringing this chaotic system into into a learning society that we can learn from different disciplines to actually find the solution. And AI or data science gives us the capability to manage this, but also just as important is to actually capture your learning as people from each other, that we can use that learning going forward. Thank you.
Right, thank you for that contribution. It is complex, beyond chaotic. It's a wicked problem, and a lot of people are trying to solve it. The problem is boundaries. We always have to draw a boundary around the system. They say, well, this is a system that we are trying to attack and solve, and but unfortunately, we overlook what's outside the system. So yeah, to what extent AI can help with that, we'll find out, and of course, this team of scientists will find out within the context of work they're doing. But yeah, thanks for that contribution. Any other questions from the audience? The gentleman in the middle.
Hi, I guess my question will direct to Dr. Robert Mead. I was very. So I was very much interested in your mortality, like minimum mortality temperature, and I was thinking, did that match with the historical mode temperature of the prosperous belt, where human civilization prospered most? Did that mode temperature match? Most frequent temperature in that belt match? Yeah.
Yes, generally speaking, and in the slide I showed where the minimum mortality temperature was very strongly related to the summer climate, the summer wet bulb temperature, that's actually not really a new finding. There's been studies looking, as you mentioned, that the most frequent temperature in a location is a very good predictor of that minimum mortality temperature. So yeah, it seems across the board, the temperature we spend most of our time in is the temperature we're probably most adapted to. Interestingly enough, if you actually look at places where we've seen a shift, we actually have data looking at a shift in the climate. There's over maybe a 25-year period, that minimum mortality temperature shifts with it. How much of that reflects physiological changes? We're very adaptable to changes in temperatures. How much reflects societal changes? Maybe increased air conditioning penetration in areas when it gets hotter. Not quite sure. But yes, as you mentioned, the temperature that is most often tends to be the temperature we do best at. Though I will add this idea of upper limit wet bulb temperatures. This is where we move away from physiological adaptation into physics. And so eventually there should be some limit, unless we can build the most efficient and powerful air conditioner. There will be some limit to that adaptation, so something to keep in mind.
Yeah, thank you for your further explanation. I guess that also sort of explains why heat wave can become a very big contributor to migration or escapes from extreme heat.
Yeah, so it's not my field, and one that is very difficult to think about. Why I bring that up, though, is, again, what's being done right now is we're looking at data coming out of areas that are very cool. Most of just like that map I showed with the epidemiological data, if you overlaid a map of where we do thermal regulatory research, it would look almost identical. And so this idea that just because we, in young adults from, again, I mentioned Penn State, but we've done these studies in University of Ottawa as well, that if this reflects how people thermoregulate in other areas, and we're just assuming that this occurs, and then what the logical conclusion is if there's millions of hours every year that we just can't be outside during, then can we live in these locations? And I just think it's a little bit irresponsible to kind of make those claims, and this is what Project Heatwave will try to do, is you take the data from across the epidemiology, the physiology, and start to think about, okay, how much wiggle room do we have in these thresholds? Because of the implications for ideas like migration.
Thank you for all the presenters for these very insightful presentations. My question goes to either Dr. Alexander or Dr. Robert regarding to the thermal physiology. As we know, our body has several coping mechanisms like using physiological adaptation to different environments. However, with this increasing temperature, or maybe even including this change in lifestyle, in the recent time, there is increasing incidence of like infertility. So this infertility, especially in men, the physiology, usually the reproductive organ of men is in a special environment where it adapts to different change in temperature. However, with this increasing in temperature or failure to adapt this thermal physiology, do you have any idea about the future incidences of this temperature rising? Because what I have read, one is like the infertility rate is increasing, the first degree infertility is increasing by 10% by 2025, and the second degree, means after having one baby, the second degree infertility is increasing by 25% by 2030. So what can you tell us about this? Thank you.
Okay, you're asking about different heat indices and the potential sort of benefit that they provide us in understanding what may happen to the human body. Sorry? Please. Yes. Please. Thank you.
It's okay, thank you. I think I'm audible. Our body is made up of proteins, right? So there are several kinds of proteins we are having. So once your body go in a sun, it adapts to some temperature, right? So what happened that, according to the study which Alex has shown in his paper, in his slide, that it was being done in the Montreal, around 22 human bodies were being taken, 15 were from the male and rest from the female, and they find it out that there are 7 biomarkers are there according to your body temperature, which reacts to it. So
Right, thank you for that question, and thank you to the lady for the answer. So I think we are at the time that we have to stop here. It's been, we've been talking about heat waves for quite a few hours, and as I said earlier, we're standing between you and your lunch. So apologies, we ran over by a couple of minutes, and hopefully we're going to continue as per program after the lunch break. And once again, thank you very much to my distinguished colleagues, all the scientists sitting on this panel. Fantastic presentations, and of course, we'll continue the conversations over the break. Thank you.
Excuse me, everyone. Sorry for this. Apparently, we have had a bit of a glitch regarding food, but I heard that now we have our food ready. No, it's going to be ready in 10 minutes, so ahead. So please bear with us. We had a problem with the truck that was that delivered our food. So we're going to shift the program, and we'll be back, say, around 13:45. So we have to meet in breakout sessions after that. Apologies. Maybe it's time to think about some AI delivering our food from here. Thank you.